हेलो एवरीवन। आज हम लोग स्टार्ट करेंगे सॉल्यूशन। सो व्हाट इज a solution? Solution is a homogeneous mixture of two or more than two component. Okay, so what is a solution? Solution is a homogeneous mixture of two or more than two component. Okay, the mixture should be homogeneous. So out of the different types of solutions, we have in our syllabus only binary solution. Only binary solution. Okay, binary solution. So by means two, that means here we have one solute and one solvent. That is what is known as binary solution. So we have one solute and one solvent. Okay, so what is a solute? Solute is that quantity which is less in a solution, and solvent is the bigger part of the solution. Okay, so we can say that the component present in excess and whose physical state is the same as that of solution is referred to as solvent. Okay, and the substance which dissolved is known as solute, and the medium in which it dissolved, the that is known as solvent. So we can define solute and solvent by different means. So if we talk about types of solution, we talk about types of solution. We have different types of solution. Solid solution. Examples are brass, bronze. Solid liquid solution. Example are solution of sugar, solution of salt. We have solid gas solution. Example is sublimation of iodine. Okay, camphor, etc. We have liquid solid solution. Example is hydrated salts, mercury in amalgamated zinc. We have liquid solution. Example is alcohol in water, benzene in toluene. We have liquid gas solution. Example is aerosol, water vapor in water, air. We have gas solid solution, that is hydrogen absorbed in palladium. We have gas liquid solution, that is aerated drinks. Okay, and we have gas solution, that is mixture of gases, or you can say air. So in solid solution, solute is solid and solvent is solid. In solid liquid solution, solute is solid, solvent is liquid. Solid gas, solute is solid, solvent is gas. Likewise, liquid is solute and solvent is solid. Liquid, both of them are liquid. Liquid gas, solvent is gas. Gas solid, solvent is solid. Gas liquid, solvent is liquid, and gas solvent is gas, and solute is gas also. So out of these different types of solutions, we mainly study about solid liquid solution, we mainly study about solid liquid solution, liquid solution, liquid liquid solution, and gas liquid solution, and gas liquid solution. These are the solutions type we mainly study. Okay. Now, if we talk about solid liquid solution, if we talk about solid liquid solution, here most of the solids dissolved in one liquid or the other to form homogeneous mixture. Okay. In such solutions, the solid is referred to as solute and liquid is solvent. So here solid is solute and liquid is solvent, the bigger part. When the amount of solute is much less as compared to the amount of solvent, the solution is referred as dilute solution. In case the amount of solute is relatively larger than liquid solution, then it is concentrated solution. Now, if we talk about liquid solution, so when two liquids are mixed together, the system may or may not be homogeneous. Depending upon the nature of miscibility, we may have different types of liquid systems. Number one, completely miscible, completely miscible, completely miscible. So when two liquids mix up together in all proportions, okay, to form homogeneous mixtures, they are said to be completely miscible. The mixing of two completely miscible liquids gives a true solution. So here in completely miscible liquids, we get true solution. Okay. So completely miscible liquids means the liquids are of the same nature. That is, they are either polar, so or non-polar. That is, if they are polar, so here in the completely miscible, that is true solution, the nature of the liquids can be polar. If you take, if you talk about example, so it will be alcohol and water, alcohol and water. So water is polar and alcohol is also polar because we have OH group there, and here oxygen is more electronegative than hydrogen. And non-polar, and non-polar. So if you talk about example, it will be benzene and toluene. So example would be benzene and toluene. Okay, toluene. So if we talk about partially miscible, liquid solution, partially miscible solution. So here in this part we can say that some liquid pairs dissolved partially in each other to form two distinct layers when mixed together. That's why the term partially miscible. One layer consists of the solution of first component into the other, while the second layer is the solution of second component into the first. Such liquid pairs are called partially miscible liquid pairs. So if you talk about example, so example क्या होगा partially miscible liquid pairs का, जैसे phenol and water. Phenol and water, these are partially miscible liquid solution. Nicotine and water. Nicotine and water. Okay, there are many more examples. So two liquids are partially miscible when the intermolecular attraction of one liquid is different from that of the other. So we can note this point. This is very important. Two liquids are partially miscible when the intermolecular attraction when the intermolecular attraction of one liquid is different from other. That's why we call partially miscible liquid solution. Now the last type would be, in the case of liquid solution, it is immiscible. Immiscible. Immiscible liquid solution. So when two liquids do not dissolve into each other and form separate layers, each layer containing a pure component, they are said to be immiscible or almost immiscible liquids. So if you talk about examples, here benzene and water are immiscible liquid solution. Okay, carbon tetrachloride and water. So carbon tetrachloride and water. Two liquids are immiscible when one is polar and other is non-polar. So in immiscible liquid solution, one is polar and other is non-polar. Okay, one is polar and other is non-polar. In case of liquid system also, the chemically alike liquids dissolves in each other. A polar liquid is completely miscible with some other polar liquids, right? Non-polar is completely miscible with non-polar liquids. Okay, so you have to remember this point. Now next is our gas liquid solution. So if we talk about gas liquid solution, it is very important because here we will learn about Henry's law, okay, for cold drinks, etc., within a short time. So The solubility of a gas in a liquid depends on several factors. Some important factors are: number one, nature of gas; number two, nature of liquid; and number three, temperature; and number four, pressure. So in the later section, we learn all of this elaborately. The nature of gas and nature of solvent are important factors. Some gases are highly soluble, while the others are less soluble or insoluble in a particular solvent, right? So here solvent is liquid, solute is gas. The most soluble gas in water is ammonia. Okay, remember this. Most soluble gas in water is ammonia. Is ammonia, which dissolves to an extent of 1300 volumes in 1 volume of water at STP. Helium is least soluble in water. Helium is least soluble in water. It dissolves only 0.01 volume per 1 volume of water at STP. The role of temperature and pressure in deciding the solubility of a gas is also significant. We will see all these natures in the later section. Okay, and solubility of a gas in a liquid increases with increase in pressure, and it decreases with rise in temperature. So we can say solubility of a gas in a liquid increases with increase in pressure. So if you increase the pressure, solubility will increase, and if you increase temperature, the solubility will decrease. Solubility will decrease. So I think तुम लोगों को समझ में आया होगा ओवरऑल इस चैप्टर में हम लोग क्या क्या चीज हम लोग यहाँ पे पढ़ने वाले हैं. ठीक है, नेक्स्ट जो टॉपिक है हम लोगों का उसमें चलते हैं. वो टॉपिक है concentration terms. Okay, concentration terms. These are let us say the amount of solute dissolved in a particular amount of solvent is known as composition or concentration of a solution. Okay, we can represent these concentration terms in different ways. So our number first is mass percentage or percentage by mass. So it is mass percentage. or percentage by mass. We term this percentage as weight percentage also. Weight percentage, that is weight by weight. Okay. So what is the definition of mass percentage? Mass percentage is defined as the mass of solute in grams dissolved per 100 gram of the solution. So let me write the definition first. Mass percentage is defined as the mass of the solute in grams dissolved per 100 gram of the solution. So from here you have to concentrate on these chapters because we are entering into the main topics of solution, and here you can expect theoretical questions and as well as mathematical questions. Okay, so let us see the mathematical expression of concentration terms. So see, if we say 10% biomass area, or if we say 10% urea, it means that 10 gram of urea are present in 100 gram of solution. Okay, this is what is important because your basics should be clear in order to solve questions from this chapter. So 10% urea means 10 gram of urea are present in 100 gram of solution. So what is the amount of solvent? Solvent is 100 minus 10, that is 90 grams. So mathematically we can write mass percentage as, so mass percentage of solute, it is mass of solute by mass percent is defined as the mass of solute in grams dissolved in 100 gram of solution. So that is mass of solute, the mass of solution into 100, right? So mass of solute plus mass of solvent multiplied by 100. Mass of solute plus mass of solvent is your mass of solution, right? So we can say mass percentage of solute is mass of solute divided by mass of solution into 100. So this is the formula you have to remember. Okay, so if we say that solute is present in very less or traces, that is in very small amounts, the concentration of solution is usually expressed in terms of parts per million. Okay, so here we can make a note. When the solute is present in very small amounts, the concentration of solution the concentration of solution is usually expressed in parts per million, that is ppm, parts per million. Okay, so the parts per million of a solute may be defined as 1 million. Million means 10 to the power 6, right? So parts per million of a solute may be defined as the mass of solute present in 1 million of the 1 million grams of the solution. So if we take example here, we can say 5 ppm calcium carbonate. What does it mean? 5 ppm calcium carbonate solution. What does it mean? It means that 5 gram of calcium carbonate are present in 10 to the power 6 gram of solution. So it's very less number, right? And if we say another example, that is concentration of oxygen in seawater is about 5.8 ppm. That means 5.8 gram of oxygen present in 10 to the power 6 gram of seawater. So I think you got the point. Our next concentration term is volume percentage. Volume percentage or percentage by volume. This is V by B. So volume percentage is defined as the volume of a solute in a particular unit present in the 100 units of the volume of the solution. So let us first write the definition, because that is, you have to remember the equations and mathematical expressions from definition. So it is defined as the volume of a solute that should be in a particular unit present in the 100 units. That is, whatever you take the unit of solute, that should be the unit of the solvent also. 100 units of volume of the solution. Okay, so if we say that 10% V by V ethyl alcohol solution, what does it mean? It means that 10 milliliter of ethyl alcohol dissolved in 100 milliliter of the solution, right? So see, both of the units are same. So we can define volume percentage mathematically volume percentage of solute, that is volume of solute by volume of solution by volume of solution into 100. Okay, here also, if the solute present in very small numbers, okay, or very small amounts, it is expressed in ppm, that is parts per million. Okay, in this case you have to remember these, the values refer to the volumes and not masses. In the mass by mass percentage, ppm refers the masses. Here ppm would be in volumes. Okay, and if we say more precisely, ppm unit is generally used to express the concentration of harmful gases in air. Okay, if we say 10 ppm sulfur dioxide gas in the air, that means that 10 centimeter cube of sulfur dioxide are present in 1 million, that is 10 to the power 6 centimeter cube, that is 10 to the power 6 centimeter cube, that is 1000 liter of air. Okay, so I think you got the point. Next concentration term is grams per liter. Grams per liter, that is G by L. So it's very easy, right? The concentration of a solution in grams per liter refers to the amount of solute in grams present in 1 liter of solution. Amount of solute in grams present in 1 liter of solution. Present in 1 liter of solution. Okay, so if we say 5 gram per liter NaCl solution, that means 5 gram of NaCl are present in 1 liter of the solution. So I think you got the point. Number 4 is molarity. Molarity, it's denoted by capital M. So what is molarity? Molarity is number of moles of solute dissolved per liter of the solution. So it is number of moles of solute dissolved per liter of the solution at a particular temperature. This is very important. At a particular temperature. Because molarity is a temperature dependent term. So remember this. molarity is defined as a fixed temperature. Okay, so and capital M solution जिसको हम लोग molar solution भी बोलते हैं, refers to the solution which contains 1 mole of a substance defined dissolved per liter of the solution. So in short, we can say molarity is number of moles of solute, number of moles of solute divided by volume of solution in liter. Volume of solution in liter. Okay, so the unit would be mole per liter. So if we say we have n moles of a solute present in V liter of the solution, we can say molarity is N by V. So this is the basic definition you have to remember. In numerator we have solute, number of moles of solute, and in denominator we have volume of solution, and that volume of solution should be in liter. And remember this, molarity is a temperature dependent term. Okay. Now elaborate this topic. If we say small w is mass of solute, this is in moles. So mass of solute in grams. Let us say V, small v, is volume of solution, volume of solution in centimeter cube. Let us say capital M prime is molecular mass of the solute, molecular mass of the solute in gram per mole, and let us say capital M is molarity of the solution in mole per liter. This is molarity of the solution in mole per liter. So what is the definition of mole? Mole is weight by molecular weight, right? So you can say N is weight by molecular weight, and this molecular weight is molecular weight of solute, right? And this weight is mass of solute. And here see we have defined small v, that is volume of solution in centimeter cube. So what would be our capital V? That would be small v by 1000. So if we substitute this in this equation, we got capital M equals to small w by capital M prime by V, small v by 1000. This is the basic equation. You have to remember this. Whatever they will ask you, you can put the values and find out the other values. So if you simplify this, you will get W multiplied by 1000 divided by small v into capital M prime. And if they ask to find out the weight, put the other values and you can find the weight. So I do not support to remember all the formulas. Comes from basics. If you know the basics, then your mental stress will be less. Okay. If you remember more and more formulas, your mental stress will be more. So try to come from basics. It is not difficult because we know the definition of moles, that is weight by molecular weight, and we have solute in the numerator. So it would be weight of solute divided by molecular weight of solute. And here in the denominator we have volume of solution in liter. And here we have assumed that small v is volume of solution in centimeter cube. So you have to divide it by 1000 to get the volume of solution in liter. So v by small v by 1000 is your capital V. So remember these two things and put in the basic formula, you will get all these things. Okay. Now, if you notice in the molarity terms, we have volumes, right? And we know volume is dependent on temperature. Volume is temperature dependent. Volume is temperature dependent. So we can say molarity of the solution is also temperature dependent. That's why in the definition we have to mention this at a particular temperature, otherwise the definition would be wrong. So you can say molarity of a solution changes with time. Molarity of a solution changes with temperature. Remember this. I am highlighting this again and again because they will definitely ask questions from this section. Now, our next concentration term is formality. So it is our number 5th concentration term. This is formality. Actually, we don't use much these formality terms because this is used for ionic compounds. So this unit is used for ionic compounds which exists in the form of aggregates formed by the ions in a solution. So ionic compounds actually do not possess discrete molecules, and the term molecular mass has no meaning for them, right? So Pauling suggests to use the term gram molecular mass in place of molecular mass for ionic compounds. So formality is used in ionic compounds. Ionic compounds. Okay. And Pauling suggested to use gram formula mass in place of gram molecular mass in place of molecular mass for such ionic compounds. Okay, that's why we have coined this term formality for ionic compounds. Okay, it is represented by capital F. Now let us write the definition first. The number of gram formula mass, it is actually molecular mass, but for ionic compounds we use gram formula mass. The number of gram formula mass of an ionic solute of an ionic solute dissolved per liter of the solution at a particular temperature is called formality of the solution. So we can define formality as number of gram formula mass, number of gram formula mass of the solute divided by volume of solution, volume of the solution in liters, in liters. Okay, and if we see from this, we can find the weight, molecular weight, mass of the solution, right? W. So here W would be m into m prime into small v by 1000. If you cross multiply all these terms to the left hand side, you will get this term, right? So if you compare with this, you will get the same weight of solute. That is, here in place of molecular mass, you will have gram formula mass, or in place of molarity, you will have formality. So you will have F, and let us say this is our M double prime. M prime is our molecular mass of solute. So here M double prime would be, let us say, our formula mass of the solute multiplied by small v by 1000. So this is W. So let me write all the terms. W is mass of solution, this is mass of solute, not solution. Mass of solute in centimeter cube. Small v is volume of solution, volume of solution. Mass of solute in gram. This is volume of solution in centimeter cube. M double prime is formula mass of the solute, and F is formality of the solution. F is formality of the solution. Okay, so we can say a solution containing 1 gram formula mass of a solute per liter of the solution has formality equals to 1 and is called formal solution. Okay, and remember one thing, This formality is also changes with temperature because we have volume terms here. So remember this formality is changed. Formality is, you can say in this manner, formality is a temperature dependent quantity, is a temperature dependent quantity. Okay. Now our number 6 concentration units, that is molality. Molality, and it is denoted by small m. So what is molality? Molality of a solution is defined as the number of moles of solute dissolved per 1000 gram or 1 kg of the solvent. So let me first write the definition. Is defined as the number of moles of solute dissolved per 1000 gram, or we can say 1 kg of the solvent, of the solvent. Okay, so it is represented in the units mole per kg. So you can say molality is number of moles of solute by mass of solvent, by mass of solvent in kg. So this implies molality is, let us say, number of moles is small n of solute, and mass of solvent in kg, let us say W, or let us say this is capital W. So N by W is what is molality. Okay, and here remember this W is in kg. Okay, so relationship would be W, if you compare with the previous two relations, we will get W is molality into M prime into W prime by 1000. This is the formula you have to remember, or you can come from basics also. So let's define each and every term. Here W is mass of solute in grams. M prime is molecular mass of the solute in gram per mole, and W prime is mass of solvent in grams, and M is molarity. Molality of the solution in mole per kg. Okay. So if we say a solution containing 1 mole of solute per 1000 gram of the solution, that should be the molality is equals to 1, right? And that is known as molar solution. In the previous case, we have defined it as molar solution. Here it is molar solution, right? So since mass of the solvent is independent of temperature, because here we have weight, molality of a solution does not change with temperature. So remember this, molality does not change with temperature. Okay. Now next term is our normality. Is our seventh number. This is normality. That is capital N. This is very important. So let me write the definition first. The number of grams equivalent, number of grams equivalent of the solute dissolved per liter of a solution at a particular temperature is called the normality of the solution. So let me omit this. I think you got the point. The number of grams equivalent of the solute dissolved per liter of the solution at a particular temperature. So it is also a temperature dependent component. Is known as normality. Okay. So its unit will be gram equivalent per liter. So in terms of mathematical relation, we can write it as N is number of gram equivalents of solute divided by volume of solution in liters. Okay. So let us first define some terms. So let small w is mass of solute in grams. Small v is volume of solution in centimeter cube. Let us say capital E is equivalent mass of the solute and N is normality of the solution. Okay, in gram equivalent per liter. And we know that number of gram equivalent of solute is mass of solute by equivalent mass. So it is W by E. Volume of solution, let us say capital V. So volume of solution is V by 1000 because it is in centimeter cube. So if we substitute in the relation, in this relation, we can say normality is W by E and V by 1000. So after rearranging, we will get W into 1000 by E into small v. So ultimately we get W is N normality multiplied by equivalent mass into V by 1000. So this is the formula we will use. And obviously you have to remember the basic formula. Never forget the basic formula because you can forget this. You cannot forget the basic formula. Okay. So normality, because as it is a volume, there is a volume terms. So you can say normality is also a temperature dependent component. Normality is also a temperature dependent component. Temperature dependent component. So if we see the relationship between molarity and normality, relation between molarity and normality. The relation is as follows. Molarity multiplied by molecular mass of solute, molecular mass of solute, that is equals to normality into equivalent mass of solute. Equivalent mass of solute. In our oxidation reduction chapter, we know how to find out equivalent mass of solute. So we'll not discuss it here. We have discussed in that lecture very elaborately how to find equivalent mass. So go through that lecture. Otherwise, you will face some difficulty here in the problems of normality. So if we say, if you can remember in this format, or if you rearrange this, you will get normality is equals to molarity multiplied by equivalent mass of solute divided by molecular mass of solute. Molecular mass of solute. Okay, this is how you can remember this formula. Our next concentration terms is mole fraction. Mole fraction. It is denoted by chi. This is not x, this is chi. This is chi. So let's see the definition. First, the mole fraction of a particular component, mole fraction of a particular component in a solution is the ratio of the number of moles of that component to the total number of moles of all the components present in the solution. Okay, so mathematically we can say mole fraction, that is chi, is equals to number of moles of the given component by total number of moles by total number of moles in the solution. Okay, so let us say we have Na moles of Na moles of component A and Nb moles of component B. Then the mole fraction of A, that is chi A, is number of moles of the given component by total number of moles, that is Na plus Nb. And if we want to find out mole fraction of B, it would be number of moles of given component, that is Nb, by total number of moles, that is Na plus Nb. Okay, So remember always, if we add these two terms, Na plus Nb, Na plus Nb will cancel out. So you can say chi A plus chi B should be 1. Okay. It's a, see, in the numerator we have, and in the denominator we will have the same unit. So this terms has no unit. And remember one thing, there is no volume terms. So mole fraction is also independent of temperature. Mole fraction is independent of temperature. Mole fraction is independent of temperature. Okay. Now our last concentration terms, that is parts per million. We have already discussed little bit about this. Parts per million is ppm. So the parts per million of a solute is the mass of the solute present in 10 to the power 6 parts by mass of the solution. So you can define ppm, parts per million of a solute, is mass of solute by mass of solution multiplied by 10 to the power 6. Okay. Remember, parts per million of a solute may also be defined in terms of volumes. Okay. Let us see some example. When the concentration of carbon monoxide, it's a harmful gas, right, exceeds 100 ppm in the atmosphere, it becomes fatal for human beings. That is, if more than 100 milliliter of carbon dioxide is present in 10 to the power 6 milliliter of air, the human life becomes at risk. Okay, always remember this. Now let us see some questions from this. So our first question is, find the mass of H2SO4 present in 100 centimeter cube of a decimolar solution. Molar solution is capital M and decimolar is capital M by 10. That is what is known as decimolar solution. Now let us see the solution. If you see, we know this relation W equals to, from molarity we know W equals to capital M into M prime into small v by 1000. You know this relation. And here given that it's a decimolar solution, that is capital M is 1 by 10. Okay. And we know molecular mass of H2SO4. So here M prime is given. We have to find out, it's not given. H2SO4 comes up to be 98 molecular mass. And volume is given, in centimeter cube. That's why we divided by 1000. It is 100 centimeter cube. So put the values here. 1 by 10 multiplied by 98 into 100 by 1000. We will get 0.98 gram. Okay. So hence 100 centimeter cube of given solution contains 0.98 gram of H2SO4. That's how you have to solve this type of question. Let us see another question. So calculate the mass of H2SO4 present in 250 centimeter cube of a semi normal solution. So it is given semi normal, that is half, and normality. We have to use the formula for normality. So we know W equals to N into equivalent mass into V by 1000. So it is given semi normal, that is N is half. Okay, and we know E equivalent mass, that is molecular mass by basicity. Molecular mass by basicity. Now what is the basicity of H2SO4? We have 2H plus. So basicity, it will transfer 2 electrons. So it would be 98 by 2. It will be 49. And volume is given 250 centimeter cube. So put all these values. So W would be half into 49 into 250 by 1000. So it would be 6.125 gram. Okay, that's how you have to solve this type of question. Now let's see another question, because the more question we'll solve, the more doubts will be clear. Find the molarity and molality of a 15% solution of H2SO4. It's given that density of H2SO4 solution is 1.10 gram per centimeter cube, and it's also given molecular mass of H2SO4 is 98. Okay, so let's see the solution. So here one important term is coined, that is 15% solution. What does it mean? So 15% solution means 15% solution of H2SO4. It implies 15 gram of H2SO4, 15 gram of H2SO4 are present in 100 gram of the solution. This is the meaning of 10% solution. So we can say mass of H2SO4 dissolved is 15 gram and mass of solution is 100 gram. Mass of solution is 100 gram. Density of solution is given. Density of solution is given 1.10 gram per centimeter cube. So let us first calculate molarity. Molarity. So what is molarity? So first of all, we have to find out number of moles. So let's find out. Moles of H2SO4 dissolved is 15. Weight by molecular weight, that is 98. So 0.153. And we know density is mass per unit volume. Mass per unit volume. So we can put mass as or volume as mass by density. Mass by density. So volume of 100 gram of solution. Volume of 100 gram of solution. What will be the volume? That is 100. That is the mass. Solution mass. And density is 1.10 gram per centimeter cube. So it is 1.10. So it will be 90.91 centimeter cube. If we divide by 1000, it will be 0.091. 0.091. If we assume that it is greater than 5, 9 is greater than 5, so 0 would be 1 liter. So what is the definition of molarity? Molarity is defined capital M. That is number of moles of solute. What is the solute here? H2SO4. Number of moles of H2SO4 divided by volume of solution in liter. Volume of solution in liter. So we have calculated all the terms. Moles we have calculated 0.153 and volume of solution is 0.091 liter. It will be 1.68 mole per liter. Okay, so we can say molarity is 1.68 molar. Now let us calculate molality. Let's calculate molality. We have just calculated moles of H2SO4, that is 0.153. So moles of H2SO4 dissolved is 0.153 and mass of water present, mass of water present in 100 gram of solution is 100, and we know that 15 gram is the weight of H2SO4. So if we subtract, so it will be the solvent, weight of solvent, that is 85 gram. In kg it will be 0.085 kg divided by 1000, right? So what is molality? That is small m, number of moles of solute by mass of solvent in kg. So number of moles of H2SO4, that is solute, divided by mass of solvent, that is mass of water in kg. See, I have told you, you can solve maximum number of questions from basic formulas. 0.153 divided by 0.085. It will be 1.8 mole per kg. So we can say molality is 1.8 molal solution. Okay, I think you have got the point how to calculate this type of questions. Now let us see another question. A solution contains 25% water, 25% ethanol, and 50% acetic acid by mass. Calculate the mole fraction of each component. Okay, so this is based on mole fraction. Let us see the solution. So let us say 100 gram of solution is given. So let 100 gram of solution is there. So 25% is water out of 100 gram, 25% ethanol, and 50% acetic acid. So we can say mass of water is 25 gram, mass of ethanol is 25 gram, mass of acetic acid is 50 gram, and molecular mass of water is 18. We know molecular mass of ethanol is 46. Please calculate. And molecular mass of acetic acid CH is 60. So first of all, we have to find out number of moles. So number of moles of water, that is N1, is 25 by 18. Moles is weight by molecular weight. It is 1.39. Number of moles of ethanol, let us say it is N2. Weight by molecular weight, that is 25%. 25 by 46. Molecular weight is 46 of ethanol. It will be 0.54. And number of moles of acetic acid, let us say it is N3. So it would be 50 by 60 is 0.83. So what is the total number? Total number of moles in solution is N1 plus N2 plus N3. That is 1.39 plus 0.54 plus 0.83. It will be 2.76. So what is the mole fraction of water? Mole fraction of water, I of water, is number of moles of water, that is N1, by total number of moles, N2 plus N3. So it would be 1.39 by 2.76, 0.503. Mole fraction of ethanol is chi of C2H5O. So N2 by total number of moles, N2 plus N3. This would be 0.54 by 2.76, 0.196. Mole fraction of acetic acid. It would be chi of CH3COOH. It would be N3 by N1 plus N2 plus N3. So 0.83 by 2.76. It will be 0.301. Okay. Now let's see our next question, which is how much water should be added to 500 milliliters of N by 2 NaOH solution to obtain a decinormal solution. So let's see the solution. Suppose X milliliter of water is required to be added for dilution. Okay. So let X milliliter of water is required to be added for dilution. We know this basic formula, N1 V1 equals to N2 V2. Okay. So here in the left hand side it is concentrated solution, and the right hand side we have assumed it is diluted solution. Okay, and it is given that for concentrated solution, it is given n by 2 of NaOH. So N1 is given half. Some volume is given 500 ml. And for diluted solution, for diluted solution, it is given that to obtain a deci normal solution. So deci means 1 by 10. That is half. Deci normal means half. So half. And what would be the V2? V2 would be 500 plus X, because we have added X milliliter of water. We have diluted. So diluted volume would be 500 plus X. And here it is given that deci normal. So for diluted solution, N2 would be half. So N1, V1, that should be N2 into V2. So by calculating, we got X is 2000 milliliter. So 2000 milliliter of water should be added to obtain a deci normal solution. So let's start our discussion with intensive and extensive properties. See, the properties associated with the bulk behavior of matter are called observable properties or macroscopic properties. Okay, these macroscopic properties of a system are of two types. So macroscopic properties are of two types. One is intensive property and another is extensive property. Extensive property. So if we talk about intensive property, the properties which do not depend upon the quantity of matter present in the system are called intensive property. So let us discuss these properties elaborately. So first is our intensive property. So these properties do not depend upon the quantity of matter. Do not depend upon the quantity of matter present in the system. Okay. See, the examples of intensive properties are temperature, density, concentration, specific heat, viscosity. These are the some examples of intensive property. All these properties do not depend upon the quantity of matter. Okay. See, temperature does not depend upon the quantity of matter. Right? If the room temperature is 25 degrees Celsius, both the small amount of water kept in a beaker and a large amount of water kept in a bucket will be at 25 degrees Celsius. So amount of quantity of matter does not depend on temperature. Temperature does not depend on quantity of matter. Okay. If we say if a solution has a concentration of 1 gram per liter, then the concentration of each drop of the solution would be 1 gram per liter, right? So temperature and concentration do not depend upon the quantity of matter and hence are intensive property. So if you take a small amount of water and large amount of water, viscosity would be same. For honey, if you take small 2 or 3 drops of honey, then viscosity, and if you take a very big quantity of honey, then viscosity will be same. Okay, and surface tension will also same for small amount of water and large amount of water. So these are intensive properties. Now let's discuss about extensive property. Let's discuss about extensive property. It depends upon the quantity of matter. So extensive property depends upon quantity of matter. Quantity of matter. Okay. So let us see some example. That is number of moles, mass, volume, enthalpy, entropy, free energy, gas free energy, all those energy are example of extensive property. See, if you see mass, if you take a block of mass m and if you divide it by half, if we divide it by half, then mass will be m by 2. So mass is a extensive property. It depends on matter. Similar is volume, similar is entropy, entropy and enthalpy, entropy and free energy and number of moles. Now let us move forward to our next topic, which is colligative property. There is no exam where they will not frame question from this topic. This topic is very important. Definitely 1 to 2 question will come in your exam, whether it is your board exam, neet exam, JEE exam, whatever. So let us see colligative property. Colligative properties. See, solutions exhibit certain very important and interesting properties. Those properties are known as colligative properties. These properties are related to the number of solute and solvent particles present in the solution and do not depend upon the nature of the solute. So let us see the definition first and let us write it. The properties of solutions which depend upon the number of solute particles, molecules or ions present in a definite amount of solvent but not on the chemical nature of solute are called colligative properties. The properties of solutions which depend upon the number of solute particles, number of molecules or number of ions present in a definite amount of solvent, but it do not depend on the chemical nature of the solute, are called colligative properties. So the definition itself explained everything about colligative properties. So if we see some important colligative properties, these are relative lowering of vapor pressure, elevation of boiling point, elevation of boiling point, elevation of boiling point, depression of freezing point, the depression of freezing point, osmotic pressure, osmotic pressure. These are some important colligative properties. So let us see these properties are very helpful in determining the relative molecular masses of non-volatile substances. Okay. Now let us discuss elaborately. Let us first see what are non-volatile, non-electrolytic and electrolytic solutes. So non-volatile substances which dissolve in water to form a solution can be classified into number one, non-electrolytic solutes, non-electrolytic solutes. These are the classification of non-volatile substances, okay, which dissolves in water. So non-electrolytic solutes, the solutes which do not ionize in solution, right? That is non-electrolytic solutes. Due to the absence of ions, their solutions do not conduct electric current. Okay, so some examples are sugar, urea, glucose, and many more. Number two is electrolytic solutes. Electrolytic solutes. Solutes which dissociate into ions, right? In aqueous solution are called electrolytic solutes. These are mostly ionic compounds and possess oppositely charged ions held together by electrostatic force of attraction, which is obvious, right? Polar covalent compounds may also act as electrolytic solutes. Due to the presence of oppositely charged ions, the solution of an electrolytic solution conducts electric current because it contains ions. And these electrolytic solutions are these electrolytic solutes are classified as strong electrolytic solutes, strong electrolytic solutes. So these are completely, or we can say almost completely ionized in solution, are called strong electrolytic solutes or strong electrolytes. These are true ionic compounds and ionize to an extent of almost 100% in the solution. So if we talk about examples, then NaCl, KCl, NH4Cl, K2SO4. These are examples of strong electrolytic solutes. And if we say weak electrolytic solutes, then these solutes do not dissociate or do not ionize completely in solution. Okay, so these are mostly polar covalent compounds. Weak electrolytic solutes are mostly polar covalent compounds and are quickly ionized into solution in solution. If we talk about example, then it is acetic acid, ammonium hydroxide, HCN. There are many more examples. Now let us see dissociation and association. What is the difference between dissociation and association? So let us first talk about dissociation. Dissociation. The electrolytic solutes are mostly ionic in nature and possesses oppositely charged ions held together by electrostatic forces of attraction. We know this. When dissolved in water, the electrostatic forces responsible for holding ions together get weakened under the influence of high dielectric constant of water and ions get separated. See, if we see the example of NaCl, this is a electrolytic solute and dissociate into ions, right? So if we see NaCl, this is Na plus, and there are electrostatic forces between Na and Cl. This is electrostatic force of attraction. Electrostatic force of attraction. If you put NaCl into water, it will dissociate into Na plus aqueous and Cl minus aqueous. The polar covalent compounds also dissociate into ions in the same way. If we talk about strong electrolytic solutes, the number of particles in the solution is an exact multiple of the number of ions present in 1 mole of the solute. If we talk about an example, when 1 mole of KCl when 1 mole of KCl containing a total of 2 moles of ions, right? If we talk about 1 mole of KCl, if we talk about 1 mole of KCl, that means here we have 2 moles of ions, 1 mole K plus and 1 mole Cl minus. So this is 1 mole of KCl aqueous. This should give 1 mole of K plus and 1 mole of Cl minus. Okay, so that is 2 mole of ions. So that means there should be no KCl present which are unionized. That is, KCl is a strong electrolyte. And in case of weak electrolytic solutes, the number of particles of the solute in the solution is not an exact multiple of ions present in 1 mole of the solute, but a part of it depending upon the degree of dissociation. Okay, this is because weak electrolytic solutes are partially ionized and the solution contains both type of ions along with the undissociated molecules, and an equilibrium exists between them. So for weak electrolytic solutes, this is for strong electrolytic solutes, and for weak electrolytic solutes, CH3 COOH aqueous plus H2O liquid. Here an equilibrium will establish between the dissociated ion and undissociated ion. So here we will get hydronium ion and acetate ion. Okay. If we talk about ammonia ion, aqueous and H2O liquid, here also an equilibrium will establish between dissociated ion and undissociated ion. NH4 plus aqueous plus OH minus aqueous. This is all about dissociation. Now, if we talk about association, certain solutes undergo molecular association in solution. That is, their molecules combine together to form aggregates. When two molecules of the solute combine together, the aggregate formed is called a dimer. The aggregate formed by the combination of three molecules is called trimer, while that formed by the combination of four molecules are tetramer, and so on. So, if we talk about benzoic acid, dissolved in benzene, two molecules of it associate to form a dimer. So when benzoic acid, that is C6H5 CHH, is dissolved in benzene, two molecules of benzoic acid formed a dimer. C6H5 CHH whole 2. There is a dimer of benzoic acid. Dimer of benzoic acid. Okay, this is a dimer of benzoic acid. So, in case of association, the number of solute particles present in solution is less than the number of particles expected to be present, because some of them group together to form particles, right? Here dimer is formed, so number of particles is less in association because two molecules are associated, right? It forms a dimer. If three molecules associate, then it will form a trimer. Okay, now moving forward, our next topic is solutions of gases in liquids. Solutions of gases in liquids. See, several gases dissolve in water. Ammonia and hydrogen chloride gas dissolve to a very large extent in water. Gases like oxygen, nitrogen, helium are soluble to a small extent only. The oxygen dissolved in water is a great biological importance, because we know, because for aquatic life, biological oxygen demand BOD is extremely necessary for aquatic life. Okay, so solubility of a gas in water depends on the nature of gas, temperature, and pressure. The solubility decreases with increase in temperature, as we have discussed in the very first of our lecture. On the other hand, solubility increases with increase of pressure, right? A quantitative relation between pressure and solubility of a gas in a solvent was given by Henry. This is known as Henry's law. Understand? A quantitative relation between pressure and solubility of a gas in a solvent was given by Henry, W. Henry, in 1803. This is known as Henry's law. So, in overall perspective, Henry's law is relation between pressure and solubility of gas, right? So, let us see Henry's law. Let us state the law first. At constant temperature, at constant temperature, this is very important. At constant temperature, the solubility of a gas in a liquid is directly proportional to is directly proportional to the pressure of the gas, directly proportional to the pressure of the gas. Okay, so we can say solubility is directly proportional to pressure of the gas. Okay, now if the solubility of a gas in a solvent is expressed in terms of mole fraction of the gas in the solution, Henry's law can be modified. So the modified Henry's law is mole fraction of a gas in its solution in a solvent is directly proportional is directly proportional to the partial pressure of the gas, partial pressure of the gas over the solution, over the solution. So Henry's law can be stated in this form also. Okay. Now there is another form of Henry's law. We can define Henry's law in this form also. The partial pressure of the gas in vapor phase is directly proportional is directly proportional to the mole fraction of the gas in the solution. We require this definition in order to express it in order to express Henry's law in mathematical form. So let us say chi is the mole fraction of the gas in the solution and P is the partial pressure. So if we say, then according to this, partial pressure should be proportional to mole fraction. So if we omit proportional, then we have to give a proportionality constant, that is kh into chi. This is Henry's law in mathematical form. Here P is partial pressure in vapor phase, and chi is mole fraction of a gas in the solution. Okay, here KH is a constant, is known as Henry's law constant. It is Henry's law constant. Okay, KH is a function of nature of gas because different gases possesses different value of KH. Okay, so from this equation it is clear that at a given pressure the solubility of a gas is inversely proportional to KH. At a given pressure, higher the value of KH, lower is the solubility of gas. So let me note it here. At a given pressure, higher the value of KH, lower is the solubility of the gas. Okay. Now, if we talk about application of Henry's law, is very important. If we talk about application of Henry's law, the solubility of gas in water increases with pressure, right? If you give more pressure, the gas will be dissolved in water more. Soft drink bottles are sealed under high pressure, right? Soft drink bottles are sealed under high pressure. This is the application of Henry's law because if you put more pressure on the liquid, more carbon dioxide will dissolve in the water, right? So that's why soft drinks are tasty because there is more carbon dioxide dissolved at high pressure. Now, next application is for scuba divers use air for respiration. Okay, for deep sea scuba divers use air for respiration. They develop a medical condition known as bends. Sometimes this come in your exam. This is bends. What is bends? This is a medical condition which involves the blocking of capillaries. Bends. It involves, or we can say, it's a medical condition. It's a medical condition which involves the blocking of capillaries, which involves the blocking of capillaries. This is because air is mainly a mixture of oxygen and nitrogen, right? According to Henry's law, the solubility of gases increases with increase in pressure. Just now we have learned this. When driver breathes air under high pressure in water, nitrogen dissolves in blood, right? When the driver comes towards the surface, the pressure gradually decreases. This releases the dissolved gases and leads to the formation of bubbles in the blood. This is quite painful and dangerous to life. In order to avoid bends this medical condition and toxic effects of dissolved nitrogen in blood, the tanks used by sea divers are filled with air diluted with helium. Remember this? This tank the scuba diver used, it come in your exam, it contains 11.7% of helium, 56.2% of nitrogen, and 32.1% of oxygen. Remember this. Okay. If we talk about next application of Henry's law, the pressure of oxygen in air decreases in going up the mountains, right? Because pressure decreases. At very high altitudes, the partial pressure of oxygen in air is much less than that at the ground level. Therefore, people living at high altitude or climbers have low concentration of oxygen in the blood, right? You go higher and higher, the dissolved oxygen will be less because pressure is less and in the tissues. This leads to weakness and loss in the clarity of thinking because there will be less oxygen in your brain. These symptoms create a condition known as anoxia. So this also come in your exam, that is anoxia. Less oxygen dissolved in blood. This is anoxia. Remember this term. And if we talk about next application, Henry's law explains the supply of inhaled oxygen to tissues. When air is inhaled, it combines with hemoglobin of the blood in lungs to form oxyhemoglobin because in lungs the partial pressure of oxygen is high. Partial pressure of oxygen is low in tissues. Hence, oxygen is released from oxyhemoglobin and is utilized by the cells. Okay. So this is the fourth of application. Oxygen is released from oxyhemoglobin and that oxygen is utilized by cells. Okay, I think you got the point. If we talk about limitations limitations. See, I am not writing everything. You have to listen to me, and if you think that something you have to write in your copy, then listen the lecture in slow mode and write everything what I am telling. Because if I am going to write everything, the lecture will be too long. Okay? So if you can remember what I am talking here, you don't have to write. But if you think that in the long term you will forget, so you can write or you can make your notes in your own way. I am just writing all the important terms here so that you can revise easily for your exam. Now, if we talk about limitations of Henry's law, if we talk about limitations of Henry's law, first limitation is Henry's law is applicable to ideas gas only. This is the first point. Henry's law is applicable to ideal gases only. However, the law can be applied to real gases at low pressure. This is very important. This law can be applied can be applied to real gases at low pressure. Remember this is very important. For real gases, you can apply this law at low pressure. When the real gases approach the behavior of ideal gases, because we know at low pressure and high temperature, the real gases behaves as ideal gas. Next limitation is this law is not applicable to those gases which undergo a chemical change in solution. The law cannot be applied to ammonia which react with water to form ammonium hydroxide. Right. So whenever there is a chemical change, you cannot apply this law. So for chemical change, this law is not applicable. Let us see next limitation. The law cannot be applied to those gases which dissociate into ions in solution. It cannot be applied to, for example, hydrogen chloride gas because it dissociates into H plus and Cl minus in solution. So we can say this law cannot be applied to those gases which dissociate into ions in solution. Okay. Now, if we talk about solid solutions, is our next topic. The homogeneous mixture of two or more solids is termed as solid solutions. These solid solutions are again divided into two types. First is substitutional solid solution substitutional solid solution, and next is interstitial solid solution. Interstitial solid solution. So if we talk about substitutional solid solutions, in this type of solutions, some of the constituent particles, let us say atoms, molecules or ions, present in the crystal lattice of one substance are replaced by the similar species of some other substance. Okay. So let us say if we want to understand this, we have one type of atom. Let us say these are one type of atom. Okay. Here in this diagram we can see that, let us say, this red dot is your solute and this, okay, let us say the solutes particles are large, so solvent particles are large here. So let us say these reds are solvent and these green dots are solute. So if you look here one type of molecules is inserted into other molecules, right? Atoms or molecules. Some of the solvent molecules are replaced by solute molecules, right? This. So if we talk about example, in this example are brass, bronze. Okay, these are the examples. And if we talk about interstitial solid solutions, this type of solid solutions consist of atoms of one substance placed into the voids or interstices present in the lattice of the some other substance, right? So let us say we have some big molecules. We have some big molecules here. We have some big molecules. And in these big molecules, some of the solute particles are trapped. Let us say these are the solute particles which are trapped. Okay, they are the solute particles which are trapped. So this is our solute particles. And these reds are solvent particles. Okay, so if we talk about examples, we can say tungsten carbide. Tungsten carbide is an example. WC. Okay. In this solution, carbon atoms occupy the interstices present in the lattice of the tungsten atom because its size is large and carbon is a very small atom. Okay. Each carbon atom is surrounded by 6 tungsten atoms in an octahedral form. Now, if we talk about our next topic, which is solutions of solids in liquids. Solutions of solids in liquids. See, at a particular temperature, only a definite amount of solid can be dissolved in a definite amount of liquid. If we take example, if we go on dissolving sugar into water at a particular temperature, a stage is reached when no more sugar can be dissolved into it. If more sugar is added, it does not dissolve and is thrown down in the form of a solid residue at the bottom of the container, right? A solution in which no more solute can be dissolved at a particular temperature is called a saturated solution. Okay, let me write it here. A solution in which no more solute can be dissolved at a particular temperature at a particular temperature is called a saturated solution. Okay, at that temperature and the amount of solute required to prepare a saturated solution in a given quantity of solvent is called the solubility of the solute at that temperature. In a saturated solution, a dynamic equilibrium exists between the molecules in the solid state and the molecules in the solution. Okay, thus a solid solution equilibrium, we can say solid solution equilibrium exists in the form of the solid in solution. There will be a equilibrium solid which are undissolved, which are undissolved. When a solid is added to a liquid, the molecular vibrations tend the molecules to pass into the liquid phase. This tendency is called dissolution. So let me write it here because it's very important. When a solid is added to a liquid, the molecular vibrations tend the molecules to pass into the liquid phase. Okay, this tendency this tendency is called dissolution. Okay, this term is very important. The molecules thus, you can say, set move freely in the liquid phase, right? As the concentration of molecules into the solid phase decreases, the dissolved molecules tend to come back to it. This tendency is called precipitation. Okay, Initially, the rate of dissolution is quite high. As the number of molecules in the solution phase increases, the rate of precipitation also increases. And after some time, a stage comes when the two rates becomes equal and an equilibrium is established. Okay, so we can say at equilibrium, we can say at equilibrium, at equilibrium, rate of dissolution, rate of dissolution is equals to rate of precipitation. Precipitation. Okay. So the solid liquid equilibrium is dynamic in nature. That is, the dissolution and precipitation process takes place simultaneously and their rates are equal in the state of equilibrium. If we draw a diagram, let us say this is our diagram, and let us say here we have undissolved solids. These are our undissolved solids. Undissolved solid. And some of the molecules, let us say this solution is saturated. This is saturated solution. And precipitation is happening. Precipitation is happening. Okay. Precipitation is happening here. This is precipitation. Okay. And this is your dissolution. Okay. The molecular vibrations tend the molecule to pass into the liquid phase. This is dissolution. So this liquid phase is, let us say, dissolution. Okay. Sorry, this is not your dissolution. The vibrations of solids, the molecular vibrations, right? So let us say some molecules are moving upward. Okay, these are vibrating. This is dissolution. Okay, because these solids are added into liquid and these molecular vibrations tend the molecule to pass into the liquid. Some of the molecules are passing into the liquid phase. So this is dissolution. Now, if we talk about dissolution, mechanism of dissolution, so let us talk about mechanism of dissolution. mechanism of dissolution. So the dissolution of a solid into a liquid can be explained either on the basis of the phenomena of solvation or on the basis of hydrogen bonding. So let us see these two methods. First is dissolution due to solvation. Okay, it's a common experience that polar substances dissolve readily in polar solvents like water, whereas they remain insoluble in nonpolar solvents. We know this. The solubility of polar solutes in polar solvents is due to solvation of their ions in the solution. Let me write the point here. The solubility of polar solutes in polar solvents is due to solvation of their ions in the solution. The phenomena of solvation refers to the development of some sort of attractive forces between the solvent and solute particles, usually referred to as solvent-solute interaction. Water, being highly polar, acts as one of the best solvents for ionic solids. When water is taken as the solvent, the solvation is termed as hydration. Okay, so when water is taken as the solvent, the solvation is termed as hydration. Okay, this is very important. Now, when an ionic solid is placed in a polar solvent, the polar molecules of the solvent orient themselves in such a way that their polar ends direct towards the oppositely charged ions of the solid. This leads to the development of a solvent-solute interaction. Okay, so if we take an example, let us see example. When a crystal of sodium chloride, so let us see the diagram first. Okay, let me draw it in this way. This is minus ion, this is minus, this is minus, Let us say this is minus, this is minus, this is minus, this is minus. Let us say this is minus and this is minus and this is plus. These reds are Na plus and these green are Cl minus. You will observe that this negative is surrounded by positive ions. This positive will surrounded by negative ions, negative side of dipole. So if you observe, this negative ion is surrounded by positive side of the dipole. This is negative side, positive side of the dipole. And this positive charge is surrounded by negative side of the dipole, negative side of the dipole. Okay, so I think you got the point. So when a crystal of sodium chloride is placed in water, we know the structure of water. As oxygen is more electronegative, it will attract the shared pair of electron towards itself. So it will be delta minus, and hydrogen, both the hydrogen will be delta plus. The polar water molecule, these are your water molecules. These are your water molecules. The polar water molecules attach themselves to Na plus and Cl minus ions of the crystal with their oppositely charged polar ends directed towards Na plus and Cl minus ions. The solvent solute. So what is the solvent? Solvent is water. And what is the solute? Solute is NaCl. The solvent solute interactions are accompanied with the release of energy called solvation energy or hydration energy when water is used as a solvent. Okay. If solvation energy is greater than the lattice energy of the solid, the solvated ions get detached from the crystal. See, here we can see that some of the Cl minus and of the Na plus are get detached. So when this phenomena happens, this happens when solvation energy is greater than lattice energy. Lattice energy, because in the lattice, in the NaCl lattice, electrostatic force of attraction is there. Okay, when dipole ion interaction is greater than electrostatic force of attraction, then this particle will get detached. Okay, so when solvation energy is greater than lattice energy of the solid, the solvated ions, that is Na plus and Cl minus, get detached from the crystal. So we can say in this scenario, the solvated ions get detached from the crystal. And pass into the solvent and pass into the solvent. Okay, the process continues and whole of solid pass into the solvent in the form of ions attached to the solvent molecules. The ions further get enveloped by a layer of the solvent molecules and get assimilated with the solvent. Such ions are called solvated ions or hydrated ions. These ions are now solvated ions because it is surrounded by water molecules, or hydrated ions when water is used as a solvent. So these are your solvated ions or hydrated ions. Okay, when water is used as the solvent. The dissolution of a crystal of NaCl is in the water is, you can show it in this manner. Now, if we explain this phenomena with hydrogen bonding, so let us see dissolution due to hydrogen bonding. Dissolution due to hydrogen bonding. Several non-polar substances such as sugar, glucose, urea also dissolve readily in water. In such cases, the dissolution is due to the formation of hydrogen bonding between water and the molecules of the non-polar substance. See, if we take an example, crystals of sugar is placed in water, hydrogen bonding takes place between the hydroxyl groups of sugar and water molecules. So, let us say this is a fragment of sugar molecule. This is a fragment of sugar molecule, and we have dissolved glucose into water, and we know water is a shows dipole nature, so it's a polar water molecule, right? There hydrogen bond will be there between O minus and H plus. So you can see that there will be a hydrogen bonding. There will be a hydrogen bonding between hydrogen and electronegative element. Okay, there is a hydrogen bonding. Due to formation of hydrogen bonding, water molecules pulls away the sugar molecule from the crystal. The molecule thus separated further gets surrounded by more water molecules because another negative charge of O minus will attach to this hydrogen bonding, right? There will be many more hydrogens and oxygens. This makes the sugar molecules to get assimilated with water and to get dissolved in the water. Now, let us move forward to our next topic, which is solubility. Okay, this is our next topic, which is solubility. See, the solubility of a solute in a solvent at a particular temperature represents the equilibrium concentration of solute in the solvent at that temperature. So if we define solubility, the definition is something like this. The solubility of a substance in a particular solvent at a particular temperature is the maximum quantity of the substance dissolved in a fixed quantity of the solvent to form a saturated solution at that temperature. The definition is the solubility of a substance in a particular solvent at a particular temperature is the maximum quantity of substance dissolved in a fixed quantity of solvent to form a saturated solution at that temperature. That is what is known as solubility. That means how much solute is dissolved, right? That is solubility. The solubility of a solid is usually expressed as the mass of the solute in grams dissolved per 100 grams of the solvent. Okay, so it can be expressed as gram per liter or mole per liter. Now if we see factors affecting the solubility, factors affecting the solubility of a solid in a liquid. The solubility of a solid in a liquid is not much affected by pressure. It depends mainly upon nature of the solute and solvent and temperature. Okay, so solubility does not affected by pressure. Number one is solubility depends on nature of the solute and solvent. Nature of the solute and nature of the solvent. Okay, see, just now we have seen that a polar substance dissolve readily in polar solvents, right? Like dissolves like, we know this, and remain almost insoluble in a non-polar substance. On the other hand, non-polar solutes are soluble in non-polar solvents. That's why we call like dissolve likes. The extent to which a polar solute dissolves in a polar solvent depends largely on the dielectric constant of the solvent. Okay, the higher value of dielectric constant helps in reducing the electrostatic force of attraction between the ions of an ionic solute. Thus, higher the dielectric constant, so we can note the point in this manner. The higher the dielectric constant, more the dielectric constant, the less will be electrostatic force of attraction between the molecules. So the higher the dielectric constant of the solvent, greater is the solubility, greater is the solubility of ionic solid in heat. The number two dependency is temperature. Okay, the effect of temperature on the solubility of a substance in a solvent depends upon whether the dissolution process is exothermic or endothermic, and this phenomena we can explain on the basis of Le Chatelier's principle. Okay, so let us describe this. When a substance dissolves with the evolution of heat, the solubility decreases with the rise in temperature, right? This is according with the Le Chatelier principle. So let me write it here because it's very important. When a substance dissolves with the evolution of heat, the solubility decreases with the rise in temperature, with the rise in temperature. Okay, when a substance dissolves with the evolution of heat, the solubility decreases with the rise in temperature. मतलब अगर कोई रिएक्शन में हीट निकाल रहा है वहां पे तुम हीट दे रहे हो तो solubility घटेगा. It's very simple, right? Let us say AB solid plus aqueous, it is in equilibrium. AB aqueous plus heat, it gives some heat. When the temperature is increased, because it is already giving heat, so if you increase the temperature, the reaction will go in the backward direction. This is according to with Le Chatelier principle. The equilibrium must shift in the direction which can counteract the effect of added heat as required by the Le Chatelier principle. Hence the equilibrium would shift in the reverse direction. Okay, so now if you increase temperature, equilibrium will shift in the left hand side. So solubility will decrease, right? Solubility will increase when the reaction go in the forward direction, but it is going in the backward direction. So when temperature is increased in exothermic reaction, the solubility decreases. Number B, when a substance dissolves with the absorption of heat, that is endothermic, the solubility increases. Let me write it here. When a substance dissolves with the absorption of heat, the solubility increases with the rise in temperature. Okay. So for endothermic reaction, let us say heavy solid plus aqueous, heavy aqueous minus heat. That means it's an endothermic reaction, and in this reaction if you increase temperature, because as the reaction requires heat and you are giving heat, so it's a favorable condition, so the reaction will move forward and the solubility increases. In this case, an increase in temperature would shift the equilibrium in the forward direction and more solute would dissolve in the solvent. Thus the solubility would increase. Thus temperature has a very much effect on the solubility. This is why the solubility of a solute in a solvent is always defined and expressed at a particular temperature. Okay, remember this. Now we will move forward to our next important topics, which is Raoult's law. Now let's see vapor pressure of solution and Raoult's law. It's a very important topic. Now we are entering into more precise topic. See, dynamic liquid vapor equilibrium is established when a liquid is taken in a closed container. Let's say we have a closed container and here we have some liquid. This is our liquid. Okay, and air from the container is evacuated. First of all, we have evacuated from this container with a vacuum pump. Let us say this is our vacuum pump. Okay, at equilibrium, the rate of evaporation becomes equal to the rate of condensation. So here you will have vapors of water. So when equilibrium is established, the rate of evaporation will be rate of condensation, right? So this is a very important point. Let me write it here. At equilibrium, the rate of evaporation becomes equal to that of condensation. At this stage, the vapor of the liquid exerts a definite pressure. These vapors will exert a pressure on the liquid surface. Okay, exerts a definite pressure provided the temperature is kept constant. So here temperature is constant. Remember this. Temperature should be constant here. Okay. This pressure is called saturation vapor pressure or equilibrium vapor pressure or simply vapor pressure. So at equilibrium, at constant temperature, at equilibrium, the vapors which exert pressure on the liquid surface is known as vapor pressure. Okay, very simple definition. So the pressure exerted by the vapor, let me write the definition. The pressure exerted by the vapor of a liquid at a particular temperature in a state of dynamic equilibrium is called the vapor pressure of the liquid at that temperature. Vapor pressure of a liquid depends upon two factors. Number one factor is nature of liquid. Nature of liquid. Liquids possessing strong intermolecular forces possesses lower vapor pressure, because obviously if you have strong intermolecular forces, the molecules will not evaporate. Okay, so if it will not evaporate, how it can exert pressure on the surface of the liquid at a given temperature as compared to those liquids which have weaker intermolecular forces. So weaker intermolecular forces, the molecules will evaporate first and it will break the bonds and it will evaporate and it will exert more pressure because we will get more number of molecules. When intermolecular forces are weak, more molecules can escape, resulting in the higher rate of evaporation. Consequently, the vapor pressure is also high. For if we take an example, at a given temperature, vapor pressure of alcohol is always higher than that of water, because the alcohol possesses weaker intermolecular forces. Okay, so I think you got this point. Now, next dependence is temperature. The vapor pressure of a liquid increases with increase in temperature. Okay, so we can make this point. The vapor pressure of a liquid increases with increasing temperature. This is because on increasing the temperature, the liquid molecules becomes more energetic and a larger fraction of molecules can escape into the vapor phase, right? And this results in an increase in the rate of evaporation and consequently the vapor pressure of the liquid increases. The addition of a non-volatile solute to a volatile solvent lower its vapor pressure. Okay, because it it blocks the evaporation process. So let me write down the point here. The addition of a non-volatile solute to a volatile solvent lowers its vapor pressure. Similarly, when a volatile liquid is added to another volatile liquid, the vapor pressure of both the liquids change significantly. The vapor pressure of a solution is governed by a very important law known as Raoult's law. Vapor pressure of a solution is governed by Raoult's law. and this is very important for this chapter, Raoult's law. Okay, so let us discuss more about effect of addition of non-volatile solute to a solvent. Effect of addition of a non-volatile solute to a solvent. Just now we have seen that if you add non-volatile solute to a volatile solvent, it lowers its vapor pressure. So when a non-volatile solute is added to a volatile liquid, that is solvent, the vapor pressure of the liquid gets lowered. Thus, the vapor pressure of a solution containing a non-volatile solute is always lower than that of the pure solvent. The lowering of vapor pressure on addition of non-volatile solute can be explained by these two diagrams. Let us say we have one diagram this. Okay. We have one diagram this. We have another diagram this. Here we have, let us say we have a jar here, and we have a jar, another jar here. Here we have only pure solvents. Okay. These are solvent molecules. Here everywhere we have pure solvents. So this is your pure solvent. Let us say we have a solution. We have a solution, and where these are our solvent particle. These are our solvent particle. Let us say these are our solute particle. Okay. So the surface area of a liquid is an important factor in deciding the extent to which a liquid gets evaporated at a particular temperature. In case of pure solvent, which is this case, the entire surface of the liquid is occupied by the liquid molecules, right? Here we have only liquid molecules. But in case of a solution, this is a solution. Okay, this is your solution. In case of solution containing a non-volatile solute, a part of the liquid surface is also occupied by the solute particles. See, these are the solute particles occupied by these are non-volatile solute particles. So this is actually blocking the below molecules to evaporate. Therefore, the area of the surface containing liquid molecules decrease in case of solution. This reduces the escaping tendency of the solvent molecules in a solution. Thus, the evaporation of solvent in a solution takes place to a lesser extent, resulting in the lowering of vapor pressure, because here we have less number of molecules evaporated, so vapor pressure will be less on the surface, right? The exact relationship between the lowering in vapor pressure and the concentration of the solution is given by Raoult's law. Now, let us see our Raoult's law. Okay. So in 1887, F. Raoult, a French chemist, studied the vapor pressure of a large number of binary solutions. On the basis of the result of his experiment, he proposed a generalization which is now known as Raoult's law. Okay. So let us see our first thing, that is Raoult's law for solutions containing volatile liquids. Okay, let us see this topic first. See, for the solutions containing two or more volatile liquids, Raoult's law is very helpful in calculating the partial vapor pressure of individual components in the solution, as well as the total vapor pressure of the solution. Okay, so what is the law? Law is, sorry, for a solution of volatile liquids, the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. Is a very important law. Let us elaborate this. If we say Pi is the partial vapor pressure, this is the partial vapor pressure of ith component, partial vapor pressure of ith component in a solution, and let us say chi of I is the mole fraction of ith mole in the solution, mole fraction in the solution, ith component, mole fraction of ith component in the solution, mole fraction of ith component in the solution. So Raoult's law is telling that it is directly proportional to its mole fraction. Partial pressure is directly proportional to mole fraction. So we can say P of I is directly proportional to phi of I. So if we omit this proportionality, so P of I would be some constant into I of I. Okay. Now if we consider the component in its pure state, then in pure state in pure state, this Pi will be Pi naught. So not in the power, noting that it is in the pure state. And in the pure state, Chi I is 1. Okay. So here Pi0, Pi naught is your vapor pressure of the ith component in the pure state. So in this case, so in case of pure ith component, we shall have 100% pure component, right? So if we have 100% pure component, so mole fraction would be 1. So if we substitute this value into this equation, we will get Pi is equals to constant multiplied by 1. Okay, and is the this thing is for pure state, so Pi is Pi naught. So Pi naught is constant, right? So if we put the value in this equation again, so we will get Pi is equals to Pi naught multiplied by mole fraction. This is your Raoult's law. This is the expression. Okay. So now we can define the Raoult's law again. For a solution of volatile liquids, the partial vapor pressure of each component in the solution at a particular temperature is equal to the product of vapor pressure of the component in the pure state and its mole fraction in the solution. Okay. Now let us say a solution is prepared by mixing two volatile liquids A and B. Okay. So let we have two volatile liquids. Two volatile liquids A and B. Let chi A and chi B be respectively the mole fractions of A and B, and let PA and PB is the partial vapor pressure of A and B. Okay, and PA naught and PB naught is the vapor pressure in the pure state. So according to Raoult's law, we can say PA should be PA naught multiplied by chi A, and PB should be PB naught multiplied by chi B, right? So if we assume that P is the total vapor pressure, so total vapor pressure let us say this is P, so this should be PA plus PB. So substituting these values, we get PA naught chi A plus PB naught chi B. Okay, this is the expression. So this equation can be used to calculate the partial vapor pressure of the component of a binary solution, right? This is for binary solution. And in the beginning of our lecture, we told that here we have only binary solution in our syllabus. So Raoult's law is applicable only when the volatile liquids are completely miscible. So let me write this point. This is very important. Raoult's law is applicable only when the volatile liquids are completely miscible. Okay. If the mixture of volatile liquid does not form a solution, the law is not applicable. Okay. So if the mixture of volatile liquids does not form a solution, the law is not applicable. Okay, it should form a solution and the liquid should be volatile. Remember these 2 points. Now let us see our B, that is Raoult's law for solutions containing non-volatile solutes. Let us see. So when the solution contains a non-volatile solute, there is no contribution of the solute to the total vapor pressure, right, of the solution. Thus, the vapor pressure of a solution containing a non-volatile solute is actually the vapor pressure of the solvent in the solution, right, because there is no solute vapor pressure, so there will be only solvent vapor pressure. So let me write it here. The vapor pressure of a solution containing a non-volatile solute is actually the vapor pressure of the solvent in the solution, because there is no solute particles. Solute particles are non-volatile here, so the contribution would be only for solvent particles, right? So therefore, if the mole fraction of the solvent in a solution decreases, the vapor pressure of the solution will also decrease, right? Because here vapor pressure is dependent on solvent only. So you can say here vapor pressure is actually for solvent molecule only. This should be vapor pressure at pure state multiplied by mole fraction of solvent. Remember this, okay? So here P naught is vapor pressure of the solvent in the pure state, vapor pressure of solvent in pure state. This is mole fraction of the solvent in the solution. Mole fraction of the solvent in solution, and P represents the total vapor pressure. This is total vapor pressure. There is no vapor pressure for solutes, right? The total vapor pressure only contributes to solvent particles. So, for a solution containing a non-volatile solute, Raoult's law can be explained as, for a solution containing a non-volatile solute, the vapor pressure of the solution at a particular temperature is equal to the product of the vapor pressure of the solvent, in pure state and its mole fraction in the solution. Since P naught is a constant at a particular temperature, this P naught is constant at a particular temperature. The Raoult's law can also be stated as, the vapor pressure of a solution containing a non-volatile solute at a particular temperature is directly proportional to the mole fraction of the solvent in the solution, right? So P is directly proportional to mole fraction of the solvent. So we can say, for binary mixture I solute, mole fraction of solute plus mole fraction of solvent is 1. So I can write mole fraction of solvent is 1 minus mole fraction of solute. Now if we put in this equation, we will get P is equals to P naught into 1 minus mole fraction of solute. This implies P by P naught is 1 minus mole fraction of solute, or we can say mole fraction of solute is your 1 minus P by P naught. So we can say mole fraction of solute is P naught minus P by P naught. Remember this. This is a mole fraction of solute. Okay. So in this equation, remember this P naught minus P, this component represents the lowering of vapor pressure. This, let me write it here. This P naught minus P, this component represents the lowering of vapor pressure in formation of the solution. And this term P naught minus P by P naught, this term is called relative lowering of vapor pressure. This is called relative lowering of vapor pressure of the solution. So we can define Raoult's law again. The relative lowering of vapor pressure, for a binary solution containing a non-volatile solute and a volatile solvent is equal to the mole fraction of the solute. Okay. Now let us see our next topic, that is ideal and non-ideal solution. When two liquids are completely miscible, they can be mixed together in any ratio, right? And the solution obtained is always homogeneous, containing only one phase. Water, alcohol, benzene, toluene, benzene cyclohexane are such liquid pairs which form homogeneous solution. So binary solution can be classified into two categories. One is ideal solution and another is non-ideal solution. Okay, so let us see what are ideal solution. What are ideal solutions? The solution of two or more completely miscible liquids is termed as an ideal solution when it obeys Raoult's law at all concentrations and at all temperatures. So let me write the definition because it is very important for exam perspective. A solution of two or more completely miscible liquids is termed is termed as an ideal solution when it obeys Raoult's law at all concentrations and at all temperatures. Okay, this is the definition of Raoult's law. Ideal solution. Sorry. Now, what are the conditions to form an ideal solution? Let us see that. Formation condition for the formation of an ideal solution. What are the conditions? In order to form an ideal solution, the components must possess identical intermolecular forces. They must be similar in structure and polarity. Okay, so here are three conditions. The components must possess identical intermolecular forces. They must similar in structure. And number three is they must be similar in polarity. Okay, note these 3 points. I'm not writing here. Two liquids, let us say capital A and capital B, can form an ideal solution only when the A and B intermolecular forces, that is forces of attraction between A and B molecules, are similar to this AB molecule. Force of attraction should be similar to AA force of attraction and or BB force of attraction, intermolecular forces. This should be same. The perfect ideal solution is rare, but several solutions exhibit nearly ideal behavior. If we take example of hexane and heptane, when mixed together in any proportion, form nearly an ideal solution. This is because the intermolecular forces between two hexane molecules are almost similar to those between two heptane molecules, or to those between a hexane molecule and a heptane molecule. Okay, so if we talk about examples of ideal solution, remember one or two examples because it may come in your exam. Number one is N-hexane and N-heptane. Okay, N-heptane. Number two, benzene and toluene. Benzene and toluene. Number three, chlorobenzene and bromobenzene. Chlorobenzene and bromobenzene. There can be other examples too, as ethyl bromide and ethyl iodide, ethylene dibromide and propylene dibromide, benzene and ethylene dichloride. These are all examples of ideal solutions. Okay. Now, if we talk about characteristics of ideal solution, we have just seen the conditions of ideal solution. Now we will see characteristics of ideal solution. Characteristics of an ideal solution. So the first characteristic is solution and its component obey Raoult's law. Okay. Each component belonging to an ideal solution and the solution itself obey Raoult's law. Okay. Now, number 2 point is the change in volume on mixing should be 0. The change in volume on mixing is 0. An ideal solution obeys the additivity rule. That is, the total volume of the solution is equal to the sum of the volumes of the individual components. Right? So, technically the partial molar volume of a component present in the solution is equal to its molar volume in pure state under identical conditions of temperature and pressure. So we can say there will be no change in volume on mixing the component. So delta V mixing is 0. This is because the nature of molecular interaction forces does not change when the components forming an ideal solution are mixed together. This is the basic reason. The molecular interaction forces does not change. That's why delta V mixing is 0. Okay. Now, number 3 point is the change in enthalpy on mixing is 0. The change in enthalpy on mixing is 0. So you can say delta H mixing is 0. When the components forming an ideal solution are mixed together, no heat is evolved or absorbed and the enthalpy of the system remains constant. Okay. Thus, there is no change in enthalpy on mixing the components. So you can say delta H mixing is 0. This is because on mixing the components forming an ideal solution, the nature of the molecular interaction forces does not change. So here is the same phenomena. The force nature of forces does not change, and here we will apply the same phenomena, that is nature of the molecular interaction forces does not change. Okay. Now we'll see graphical representation of the behavior of ideal solution. Graphical representation of the behavior of an ideal solution. So let us see the graphical representation of ideal solution. Let me draw the graph here. In one side, let me draw the graph. This graph is extremely important. So remember this. So let us explain this graph. In the x-axis we have mole fraction, in the y-axis we have vapor pressure. Okay. So let us say suppose two liquids A and B are mixed together to form an ideal solution. Let chi A and chi B be their mole fractions, P and P be their partial vapor pressures, and Pa naught and Pb naught are the vapor pressures in pure state. So according to Raoult's law, we can say Pa should be chi A multiplied by Pa naught, and Pb should be chi B into PB naught. The total vapor pressure P of the solution would be is the total vapor pressure, that is PA plus PB. Okay, so chi A PA naught plus chi B PB naught. Okay, now we know chi A plus chi B is 1. Chi A plus chi B is 1. So from this we can substitute chi A as 1 minus chi B. So it would be 1 minus chi B PA naught plus chi B into PB naught. Okay, so let's multiply. It will be PA naught minus chi B into PA naught plus chi B into PB naught. So if we take common chi B, it will be PB naught minus PA naught into chi B plus PA naught, that is total pressure. Okay, now see, we know that PB naught and PA naught are constants, right, at a particular temperature. PB naught and PA naught are constant. So this is in the form y equals to mx plus c, which represents a straight line. The graph obtained on plotting vapor pressure on y-axis against the mole fraction in the x-axis. Okay, and is characteristics of an ideal solution of two miscible liquids. This graph is known as p-chi graph of ideal solution of two completely miscible liquids. Okay, so this p-chi graph consists of three straight lines, right? One is this, one is this, and one is this. RQ, so RQ straight line, PS straight line, and RS straight line. This is RS straight line, the thick line. The dotted lines RQ is plot of this y equals to mx. This is the plot. This is the plot of RQ. Okay, and gives the partial pressure of A. This gives the partial pressure of A in the solution at different mole fractions. At point R, this is the point R. At point R, when chi A is 1, if you put chi A is 1 in pure form of A, the vapor pressure would be PA would be PA naught, right? As the mole fraction of A decreases, here in the right hand side, if you move forward in the right hand side, the mole fraction of A will decrease, right? There is a mole fraction here. The mole fraction is 100%, 1. So if you move in the right hand side, the mole fraction of A decreases. The vapor pressure as mole fraction is, as mole fraction decreases, the vapor pressure will also decrease, right? Because PA naught is constant, so PA is directly proportional to chi A. So at mole fraction decreases, the vapor pressure will also decrease. Okay, and becomes 0 at point Q. Here chi A is 0, if you can notice. Okay, similarly, curve PS is the plotting of PB equals to chi B into PB naught. Okay, this gives the vapor pressure of B at various mole fractions. The curve Rs represents the total vapor pressure of the solution, and this Rs is the total vapor pressure. If you notice, this is Pa plus Pb. We have added these two component, added this two component, we get this. Added this twice, we get this. Added this component and at this height, we get this. So Rs is the total vapor pressure. That is Pa plus Pb are different mole fractions. Since and this Rs graph is given by this equation. Since liquid B is assumed to be more volatile than A, okay, we have assumed here that liquid B is more volatile than A. So the vapor pressure of the solution increases as the mole fraction of B decreases. Mole fraction of B, when mole fraction of B decreases, vapor pressure increases, right? So when mole fraction increases, vapor pressure also increases for this graph. Okay, so from this graph we can find out Pa, Pb and P, total partial pressure. So for binary ideal solution of any composition is intermediate between Pa0 and Pb0. Okay, the vapor pressure of the components in the pure state forming an ideal solution. So I think ये जो ग्राफ है ये तुम लोगों को समझ में आ गया हो. So let's start our next topic, which is non-ideal solution. Non-ideal solution. So the solution which do not obey Raoult's law are called non-ideal solution. The solution which do not obey Raoult's law are known as non-ideal solution. Okay, so non-ideal solutions are formed by those liquids whose molecules interact with one another with different forces, right? As compared to the force with which their own molecules interact mutually. So there should be different forces between intermolecular atoms. Thus, two liquids A and B form a non-ideal solution when the forces of attraction between A and B molecules are different from the forces of attraction between AA and BB molecules. Okay, understand? Now, let us see characteristics of a non-ideal solution. Characteristics of, you already know that non-ideal solution do not obey Raoult's law. So a non-ideal solution as well as the components forming it do not obey Raoult's law. Thus, for two liquids forming a non-ideal solution, we must have the partial pressure should not be equal to this Pa naught in pure form multiplied by chi of A, and P of B should not be equal to Pb naught chi of B. Okay, and total pressure should not be equals to Pa naught chi of A plus Pb naught chi of B. Okay, so the vapor pressure of such a solution is different from that calculated on the basis of Raoult's law. Number 2 point is the change in volume on mixing is not equal to 0. The change in volume on mixing is not equal to 0. Okay, because the forces are different, right? Not equals to 0. When two liquids forming a non-ideal solution are mixed together, a definite change in volume is observed. Here, a definite change in volume will be observed. The change in volume on mixing the components of a non-ideal solution is because of difference in AB molecular interaction forces and AA-BB molecular interaction forces. Okay, here AB molecular interaction forces should be different from AA molecular interaction forces or BB molecular interaction forces. Number 3 point is the change in enthalpy on mixing is not equals to 0, and the reason would be same reason. So let me write the point. The change in enthalpy on mixing is not equals to 0. So we can say delta H mixing not equals to 0. Since AB molecular interaction forces are different from AA molecular interaction forces and BB molecular interaction forces, some heat is either evolved or some heat may be absorbed when the components A and B forming a non-ideal solution are mixed together. That means it should be either exothermic or endothermic. Okay, so if we take an example, when sulfuric acid and water are mixed together, a large amount of heat is evolved. Okay, and a change in volume is observed. So if we move forward to part B, types of non-ideal solution. Types of non-ideal solution. So let us see the types. It can be divided into two categories. Number 1, solutions. This is a very important topic. Solutions showing positive deviation from Raoult's law Okay, so a solution is said to show positive deviation from Raoult's law when at any composition its vapor pressure is higher than that given by Raoult's law. It's as simple as that, right? So let me write it here. A solution is said to show positive deviation from Raoult's law when at any composition its vapor pressure is higher than that of that given by Raoult's law. Okay. So on a partial pressure versus mole fraction graph, the composition curve of such a solution lies above the composition curve obtained on the basis of Raoult's law. So non-ideal solution falling under this category can be further divided into two types. Number one, type 1 solution. Type 1 solution. So what is type 1 solution? When the vapor pressure of a solution at any composition is somewhat higher than that calculated on the basis of Raoult's law, but at no composition it exceeds the vapor pressure of the more volatile components in pure state, is said to belong to the category of type 1 non-ideal solution. So let me write the definition first, then we will see it in graphical representation. So when the vapor pressure of a solution at any composition is somewhat higher than that calculated on the basis of Raoult's law, but at no composition it exceeds the vapor pressure of the more volatile component in pure state. In pure state. So we can say this type of solution is belongs to type 1 non-ideal solution. So let me draw the graph first, then we will see, we will match this definition. So graph is Here mole fraction is 1 of A, mole fraction of B is 0, mole fraction of B is 1, and mole fraction of A is 0. So here in the y-axis we have vapor pressure, and in the x-axis we have mole fraction. Okay, so we have seen the Raoult's law. The graph looks something like this. This is our graph. Okay, let me tilt the graph more. So this is our ideal case we have seen. This is our PA naught. This is our PB naught. This point is our P. This is Q. This is R point, and this is S point. Now it shows a positive deviation. Okay, it shows a positive deviation, something like this. It should not exceed this line. Okay, B also shows this and this line. So this is 1, this is our 2, this is our third graph. So let us see one by one. Here remember, temperature is constant. Always temperature remains constant. So from this pki diagram of a type 1 non-ideal solution, there is a graph. In this diagram, the dotted line curves are obtained on the basis of Raoult's law we have seen in the previous slides. The thick curve, this now we have drawn in the blue color. 1, 2 and 3 are the observed composition curves. So the vapor pressure curve 3, this 3 curve, lies above the curve RS, right? This lies above the curve RS, this. That is, at all composition, the vapor pressure of the solution is higher than that given by Raoult's law, right? It is higher. It is also clear from this diagram that at no composition, the vapor pressure of solution exceeds PV naught. Okay, it should not exceed PV naught. The vapor pressure of the more volatile component in the pure state, it should not exceed the value of more volatile component. Here we have assumed that this is PV is our more volatile component. More volatile component. In type 1 solution, the graph will move upwards. The observation is something different from the Raoult's law, but it should not exceed the more volatile component. In our case, it is PV. As the curve 1 and 2 lie above the dotted line curve, see, curve 1 and curve 2 are lie above the dotted line curve. The RQ and RS, it is clear that the vapor pressure of the individual components A and B of the solution also show positive deviation, right? So vapor pressure of A also show positive deviation, or B also show positive, B also show positive deviation, A also show positive deviation from Raoult's law. And remember this example. Example is water and methyl alcohol. Water and methyl alcohol. So this is for PB and this is for PA. Now let us see our type 2 solution. B is type 2 solution. So these solutions also show a positive deviation from Raoult's law, but their pKi diagram show a maxima at a certain composition. Okay. In other words, at a particular composition, the vapor pressure of such a solution is higher than the vapor pressure of its individual constituents in pure state. Here, this is not possible, but for type 2 solution, it is possible. So, let us see the graph of this. It will be almost same. There is a slight difference that it can exceed the more volatile liquids. The vapor pressure can exceed the more volatile liquids. That is the only difference. So, chi A 1 here, chi B 1 here. This is your mole fraction, and this is your vapor pressure. Let us draw the, let us draw the graph. This is your ideal case. Okay, it's a straight line. This is your ideal case. Here the graph shows our maximum composition, maxima at a certain composition, and at a particular composition the vapor pressure of such a solution is higher than the vapor pressure of its individual constituents in pure state. That is, it can exceed PA naught and PB naught. Okay, so this is our graph. This is our graph. It's for PB, and this is for total pressure. So this is one first curve, this is second curve, and this is third curve. And temperature is always constant. Okay. So in this diagram, the vapor pressure curve 3, if you observe this curve 3, has a maxima, let us say at point M, let us say in this point, it has a maxima. Okay. So at this point, in this point, we have a maxima. We see it is the maximum height from x-axis. maxima, and at this point the vapor pressure of the solution is higher than both PA0 and PB0. Okay, this point is higher than PA0 and also PB0. But here in this case it is not higher. This graph is not higher than PB0. Okay, because it is a more volatile liquid in the pure state. So I think you got the point. And here for type 2 solution, the example is water and ethyl alcohol. Here water and methyl alcohol. Here water and ethyl alcohol. Okay. There are many more examples which show positive deviation from Raoult's law. So I am telling all the examples. If you want to write, you can write. Water and methanol, water and ethanol, carbon tetrachloride and benzene, carbon tetrachloride and chloroform, carbon tetrachloride and toluene, acetone and carbon disulfide, acetone and ethanol, and acetone and benzene. Okay. Now what is the reason to show positive deviation? Let us see that explanation for positive deviation. So what can be the explanation? See, the positive deviations are shown by those liquids liquid pairs for which the AB molecular interaction forces are weaker than AA and BB molecular interaction forces. So here AB molecular interaction forces are weaker than the AA or BB molecular interaction forces. Okay, when AB molecular interaction forces are weaker, the molecules of A or of liquid B find it easier to escape from the solution than from the pure components, right? This molecule will escape earlier than AA molecules and BB molecules. Okay, this is the main reason. This results in an increase in the vapor pressure of the solution because these molecules will evaporate first. It will break first, right? So it will create more vapor pressure. Thus, such a solution exhibits a higher vapor pressure in comparison to that predicted by Raoult's law and show a positive deviation from Raoult's law. Okay. Now, if we take an example, let us say we have ethyl alcohol and cyclohexane. Ethyl alcohol and cyclohexane, which shows positive deviation from Raoult's law. In ethyl alcohol, the molecules are held together through hydrogen bonding. Okay. If we see ethyl alcohol, let's see, C2H5OH, right? And it is hydrogen bonded with another ethyl alcohol. In this manner, it is hydrogen bonded, right? So, and when cyclohexane is added to ethyl alcohol, the molecules of cyclohexane try to accommodate themselves between ethyl alcohol molecules. This results in the breaking of some hydrogen bonds and weakening of the alcohol-alcohol molecular interaction forces, right? This hydrogen bond will break if we add cyclohexane. Thus, the escaping tendency of the molecules from the solution increases, and the solution shows a higher vapor pressure than that predicted on the basis of Raoult's law. For solutions showing positive deviation from Raoult's law, it should be delta H mixing should be greater than 0, and delta V mixing should also greater than 0. Okay. See, since the AB molecular interaction forces are weaker than AA and BB molecular interaction forces, more energy is required to overcome AA and BB interaction forces than that released in the setting up of AB interaction forces during the formation of the solution. Hence, the dissolution process is endothermic. Okay. So, in this dissolution process is endothermic. It requires heat to break the bonds. So, dissolution process is endothermic, and heat is absorbed during formation of such a solution. This is why delta H mixing is positive, right? And since AB molecular interaction forces are weaker, the molecules will be loosely held, and therefore there will be increase in volume. That's why delta V mixing is greater than 0. Okay, and it is positive. So let us now see our next part, which is solutions showing negative deviation from Raoult's law. Okay, so when the vapor pressure of a solution is lower than calculated on the basis of Raoult's law, the solution is said to show negative deviation from Raoult's law. So it is opposite from the previous section. Just we have learned. Even the vapor pressure of the individual components of such a solution show negative deviation from Raoult's law. So if we see the partial pressure versus mole fraction graph, let's see the graph. So let us say this is our ideal nature. This is our ideal nature according to Raoult's law. Here we will have partial pressure. In the x-axis we have mole fraction. Here we have chi A equals to 1. This is chi B equals to 1. Okay. Now here it will show negative deviation. So that means the graph will be something like this. It is showing negative deviation. Okay, and it will show negative deviation for individual graphs also. This is the graph. Okay, this is our graph 1, this is 2, and this is 3. This is our PA naught, this is our PB naught. Here is the graph. So from this graph we can see that the vapor pressure curves 1 and 2 of individual components, that is Xa and Xb, lie below the dotted line curves. Right, let us name this PQRS. Okay, so it is lie below the dotted line RQ and PS obtained from Raoult's law. The vapor pressure curve of the solution, this is the solution vapor pressure curve, also lie below. This is our calculated vapor pressure. Okay, and this is for Raoult's law. According to Raoult's law, is the solution vapor pressure below the ideal solution curve RS. The vapor pressure curve of the solution shows a minimum at point M. Let us say this is our minimum point M, because this height is minimum from all other points, where its vapor pressure is lower than that of both A and B. Okay, in the pure state. So this M point is our minimum point. Is our minimum point. So if we see some examples of showing negative deviations, the examples would be water and hydrochloric acid, water and nitric acid, chloroform and benzene, chloroform and ether, chloroform and acetone, acetic acid and pyridine, acetone and aniline. Okay, so you have to remember 1 to 2 examples. Now, what is the explanation for negative deviation? So let us see the explanation. The negative deviation are shown by those liquid pairs for which the AB molecular interaction forces, AB molecular interaction forces are stronger than the AA or BB molecular interaction forces. Okay, so your AB molecular interaction forces should be stronger than AA and BB molecular interaction forces. That's why it evaporates less and the graph shows negative deviation. When AB molecular interaction forces are stronger, the escaping tendency of the molecules of A for those B in solution is lowered as compared to that in the pure state. It will escape more. Okay. Thus, a lesser number of molecules of A and B are able to escape from the solution, which is obvious. This results in a decrease in the vapor pressure of the solution. Thus, the solution exhibits a lower vapor pressure in comparison to that predicted on the basis of Raoult's law and shows a negative deviation from Raoult's law. If we take an example in this case, so let us consider a solution of acetone and chloroform. Acetone and chloroform. If we take this example, it will show a negative deviation from Raoult's law. When the two liquids are mixed, that is acetone and chloroform are mixed together in any proportion, their molecules gets linked together through hydrogen bonding. So this is the main reason, and it will definitely come in your exam. Here in acetone, this is our acetone, CaCO3. It will be bonded with hydrogen bonding to chloroform, CCl3, CaCl3. Okay, here you will have a hydrogen bonding. This is the reason in solution it will evaporate less, so vapor pressure will be less. The formation of hydrogen bonding decreases the escaping tendency of the molecules of both acetone and chloroform in the solution, because now they are bonded with hydrogen bonding. This results in the decrease of vapor pressure, and the solution records a lower vapor pressure as compared to that predicted on the basis of Raoult's law. Okay, so for solutions showing negative deviation, you have to remember that for negative solution, delta H mixing is less than 0 and delta V mixing is also less than 0. Remember this. This will help in your exam. See, if we give the explanation for this, since AB molecular interaction forces are stronger than AA and BB molecular interaction forces, the energy released in the setting up of AB interaction forces is greater than that absorbed in overcoming the AA and BB interaction forces, right? Thus, dissolution process is exothermic. So from this we can say, or from the explanation we can say that dissolution process is exothermic. In the previous section it was endothermic, right? So that's why delta H mixing is less than 0. And since AB molecular interaction forces are stronger, the molecules of A and B will be held more tightly in the solution. This results in a decrease, because in the AB mixing, in the AB, when the solution is formed, here in this case, if you notice that it is bonded with hydrogen bonding, so the volume will decrease in the solution. That's why delta B mixing is less than 0. So I think ये तुम लोगों को समझ में आ गया होगा. Now let us move forward to our next topic, which is fractional distillation and azeotropic or constant boiling mixture. Principle of fractional distillation and azeotropic or constant boiling mixtures. Let's see. So here the components of a solution containing two or more miscible liquids are usually separated by the technique known as fractional distillation. Okay, remember this. The solutions containing two or more miscible liquids are separated by fractional distillation. Fractional distillation is based on the fact that the vapor obtained on boiling a binary solution contains a higher percentage of more volatile liquids. When the vapor is condensed, a distillate richer in more volatile component is obtained. The distillate thus obtained, okay, the distillate thus obtained boils at a temperature different from that at which the original solution boils. However, this is not true for all binary solutions. Several binary solutions are definite composition at definite composition distill over without any change in composition. The distillate obtained on fractional distillation of such a solution has the same composition and the same boiling point as that of the original solution. Such solutions are referred to as azeotropic mixtures. मतलब यहाँ पे बॉइलिंग पॉइंट सेम है. ओके, इस टाइप का सॉल्यूशन को अगर अलग करना है तो क्या टेक्निक लगाएंगे, और जिसका तुम्हारा बॉइलिंग पॉइंट सेम होगा, कंपोजिशन सेम होगा, उस टाइप का जो मिक्सचर होता है उसको हम लोग आइसोट्रॉपिक मिक्सचर बोलते हैं, और इसको हम लोग कांस्टेंट बॉइलिंग मिक्सचर भी बोलते हैं. ओके, so let us see the definition and let us write it down. The solution of completely miscible liquids which boils at a constant temperature like a pure liquid and distills over there should be one ls and distills over without any change in composition is called azeotropic mixture और constant boiling mixture. तो जो नॉर्मल सॉल्यूशन का मिक्सचर होता है वहाँ पे एक मिक्सचर का एक कंपोनेंट का बॉइलिंग पॉइंट हायर होता है, तो वहाँ पे हम लोग फ्रैक्शनल डिस्टिलेशन से उसको अलग कर सकते हैं। तो जहाँ पे बॉइलिंग पॉइंट सेम होगा और मिक्सचर भी सेम रहेगा, ओके, मिक्सचर का जो कॉम्पोजिशन है वो सेम रहेगा, तो वहाँ पे अलग करना थोड़ा मुश्किल हो जाएगा। उस टाइप का मिक्सचर को हम लोग एजोट्रोपिक मिक्सचर बोलते हैं। Since an azeotropic mixture distills over without any change in composition, the components of an azeotropic mixture can never be separated by fractional distillation, right? It's obvious. If we take an example, a mixture of ethyl alcohol and water containing 95.57% alcohol is an azeotropic mixture. These solutions will boil at 351.15 Kelvin, and the distillate obtained on fractional distillation always contains the same percentage of alcohol, that is 95.57%. Thus, alcohol and water cannot be separated from the mixture by fractional distillation. Azeotropic mixtures are formed by non-ideal solutions, that is, which do not obey Raoult's law. As we have seen earlier, we have discussed this, that the non-ideal solutions are those solutions which show either positive or negative deviations from Raoult's law. The solutions showing positive deviations from Raoult's law are of two types, type 1 and type 2 non-ideal solutions. Type 1 non-ideal solutions do not form azeotropic mixtures at any composition and distills over with a definite change in composition. So let me write it here because it is very important. The type 1 non-ideal solutions do not form azeotropic mixture at any composition and distill over with a definite change in composition. Okay, therefore, the components of type 1 non-ideal solutions can be separated completely by fractional distillation. So, for type 1 solution, it can be separated by fractional distillation. However, the type 2 non-ideal solutions form azeotropic mixtures at definite intermediate compositions. Such solutions form minimum boiling azeotropic mixtures, type 2 solution. Okay. On the other hand, the non-ideal solutions showing negative deviations from Raoult's law form maximum boiling azeotropic mixtures. So type 2 mixture shows minimum boiling azeotropic mixtures, and negative solutions showing negative deviations, non-ideal solutions showing negative deviations form maximum boiling azeotropic mixtures of definite intermediate composition. Okay, now let us discuss this one by one. So our number one point is minimum boiling azeotropic mixtures. Minimum boiling azeotropic mixtures. See, this type of azeotropic mixtures are formed by type 2 non-ideal solutions. So it is formed by type 2 non-ideal solution, which type 2 non-ideal solution which show positive deviation from Raoult's law. From Raoult's law, and at a certain composition. At a certain composition, their vapor pressure are higher than those of the more volatile component. Right? We know this from type 2 non-ideal solution. So we have already seen the graphical representation. So if we show the graph, we'll observe that uh, of a for a type 2 non-ideal solution, it shows a maxima. Right? We have seen that we got a maxima at m point, right? Which corresponds to a definite composition. This maxima corresponds to a definite composition. Here chi A is 1, chi B is 0. That is, here we have 100% of A. Here chi B is 1, chi A is 0. That is, here we have 100% of B. So here this maximum point having higher vapor pressure, right? So as the solutions having higher vapor pressure, it will boils at lower temperature. Okay. So let me write it here. Since the solution having a higher vapor pressure, so it will boil at lower temperature. Higher vapor pressure boils at lower temperature. It will boil at lower temperature. The boiling point of the solution at point M would be minimum, because for temperature graph it would be minimum, right? Because it boils at lower temperature. Even less than the boiling point of pure components. If a graph is plotted between temperature, that is boiling points, and composition, both for solution and vapor, here we will see, here we are drawing a temperature versus mole fraction graph. This is our temperature versus mole fraction graph. Okay, and this graph is for type 2 non-ideal solution. So it is clear that, let us draw the graph first. This is our solution. This is TA. This is TB. This thing is for solution. Okay, and this thing is for vapor. Vapor. Now see, it is clear that the solution becomes azeotropic at point M. At this point, the solution has the same composition as that of the vapor, right? Only at this point, vapor and solution has the same composition. Therefore, distill over without any change in composition. Moreover, at this point M, the solution has the minimum boiling point. If you see the temperature, it will be minimum boiling point. The boiling point being much less than the boiling point of TA. Here is the TA boiling point, and TB temperature is for boiling point of B, boiling point of A and boiling point of B. T would be in the higher state, okay, and TB is slightly less than TA. We have assumed that here boiling point of A is higher than boiling point of B. So the solution has the minimum boiling point, the boiling point being much less than the boiling point of TA and TB of the individual pure components. This is for A and this is for B. Thus, the solution corresponds to point M is a minimum boiling azeotropic mixture. So this is minimum boiling azeotropic mixture. Okay. If we see some example, let us say water and ethanol. Here mass percentage. Let me give one example. Here we have components. Here we have mass percentage of B, and here we have boiling points. That is in Kelvin. So if we talk about components A and B, and it is mass percentage of B, and let us say boiling point for pure A, pure B and azeotropic mixture. This is pure A boiling point, this is pure B boiling point, and this is azeotropic mixture boiling point. If we see example, let us say A, component A is H2O and it is ethanol. Here mass percentage of B is 95.57%. So alcohol is much. In pure state, water has a boiling point of 373 Kelvin. And in pure state B, the alcohol has a boiling point of 351.3. Okay. But in azeotropic mixture, the mixture will boil at 351.15. That's why it is less than pure form. So it is known as minimum boiling azeotropic mixture. Okay, understand? Let us see other examples. These are experimental data, so it will clear your doubts. Let us say we have water and we have C3H7OH. Here mass percentage of B is 71.69%. In the pure state, water has 373, that is 100 degrees Celsius boiling point, and this propyl alcohol is 370.19 Kelvin. and in the mixture it will be less than both, 360.7. So I think you got the point, how why it is minimum boiling point azeotropic mixture. Okay, now let us move forward to our next point, that is maximum boiling azeotropic mixture. Let us draw the graph first, because from the graph it will be clear. So let us say this is our vapor. Let us say this is our solution. This is our solution. This is our solution. This is your vapor. This is your vapor. Here in the y-axis we have temperature. In the x-axis we have mole fraction. Here mole fraction of A is 1, and here mole fraction of B is 1. And this is your point M. So these type of azeotropic mixtures are formed by those non-ideal solutions which show negative deviation from Raoult's law. Okay, we have seen the graph already. So the graph shows for such solution a minimum at point M. Okay, at this point the vapor pressure of a solution is minimum. At this point the vapor pressure of a solution is minimum. So if we see the negative boiling, negative deviation from Raoult's law, we have seen that we got a point M where uh, the partial pressure of the solution is least, right? It is lesser than PA naught and PB naught, that is in the pure state form. So at this point M, the vapor pressure of solution is minimum, corresponds to a particular composition. Therefore at point M the solution must possess a maximum boiling point, because it has the least vapor pressure. As it has the least vapor pressure, sorry, as it has the least vapor pressure, that means it will have more boiling point. Least vapor pressure, that means vapors are less. Okay, why the vapors are less? Because the solutions are stronger, right? So as the solution is stronger, that is intermolecular, here we have seen an example, hydrogen bonding is there. So to break this hydrogen bonding we need to give extra energy. So that means boiling point is higher for negative solutions. Okay, have you got the point? So you can say that at point M the vapor pressure will be maximum. Boiling point will be maximum, vapor pressure is minimum. Okay, so this is our temperature. So this is our TA in pure form. This is our TB in pure form, in pure state. So from this graph, it is clear that the solution becomes azeotropic at point M. At this point, the solution has the same composition as that of vapor and therefore would distill over without any change in composition. Moreover, at point M, the solution has maximum boiling point, right? You can see it has maximum boiling point. Yes, maximum boiling point. The boiling point being much higher than the boiling points of pure state of A and B. Okay. Thus, the solution corresponds to point M is a maximum boiling azeotropic curve. Right. That's why that's the name, a maximum boiling azeotropic mixture. So if we see some example, because it will be clear more. So this is our component A and B. Just a mass percent of B, we know. This is boiling point in Kelvin. Boiling point in pure form of A, pure A. Boiling point in pure form of B, and in azeotropic mixture. In azeotropic mixture. Let us take some example. If we have, let us say, H2O, and if we have HCl, so mass percentage of HCl is 20.3%, and pure form of A, that is boiling point of water, is 100 degrees Celsius, that is 373 Kelvin, and boiling point of HCl is 188 Kelvin. But if we mix them, the boiling point would be 383. See, it is higher than 373 and 188. Okay, this is the graph we have seen. So it actually explains the graph more easily. If we take another example, let's say H2O and HNO3. HNO3. Mass percentage of B is 68, and pure form of A is boiling point is 373, and it is 359 for B, and for mixture it will be 392.5, that is higher than both of them. Okay, now let us see some question. Let's see the question. Two liquids X and Y on mixing form an ideal solution. At 30 degrees Celsius, the vapor pressure of the solution containing 3 mole of X and 1 mole of Y is 550 milligram of Hg. Okay, containing 3 mole of X and 1 mole of Y. The vapor pressure millimeter Hg, not milligram, millimeter Hg. But when 4 mole of X and 1 mole of Y are mixed, the vapor pressure of the solution, the vapor pressure of the solution thus formed is 560 millimeter Hg. What would be the vapor pressure? What would be the vapor pressure of pure X and pure Y at this temperature? So let's see the solution. See, the question is two liquids X and Y on mixing form an ideal solution. At 30 degrees Celsius, the vapor pressure of the solution containing 3 mole X and 1 mole Y is 550 millimeter Hg. But when 4 mole of X and 1 mole of Y are mixed, the vapor pressure of the solution is 560 millimeter Hg. What would be the vapor pressure of pure X and pure Y at this temperature? So it's very easy. Let us see the solution. So let us say the vapor pressure of pure X and pure Y is Px naught and Py naught. Let vapor pressure of pure X and pure Y are Px naught and Py naught. Okay. So here we have two solutions. So let us see for first solution. For solution 1, so mole fraction of X is, it is given that 3 mole of X and 1 mole of Y. So mole fraction of X would be 3 by 3 plus 1, that is 3 by 4. Mole fraction of Y, that is chi of Y, would be chi X plus chi Y is 1. So chi Y would be 1 minus 3 by 4, that is 1 by 4. And total pressure is given 550 millimeter Hg. Okay. And for solution 2, for solution 2, chi of X, mole fraction of X is given, see, 4 mole of X and 1 mole of Y. So it would be 4 by 4 plus 1. This is 4 by 5. And chi of Y would be 1 minus 4 by 5, that is 1 by 5. And total pressure is given 560 millimeter Hg. Now it is given that mixing of X and Y forms an ideal solution. So ideal solution means it will obey Raoult's law, right? So we can say it will obey Raoult's law and total pressure would be Vx not chi X plus Py naught chi y. Okay. So for solution 1, total pressure is 550. That is Px naught into chi x is 3 by 4 plus Py naught chi y is 1 by 4. This is for solution 1. And for solution 2, it is 560 and Px naught into chi x is 4 by 5 plus Py naught chi y is 1 by 5. Okay. Now if we solve these two equations, two unknown, Px naught and Py naught, please solve. You will get Px naught as 600 millimeter He and Py naught as 400 millimeter He. Okay, so hence the vapor pressure of pure X and pure Y at 30 degrees Celsius is 600 millimeter He and 400 millimeter He. Now let us see another question. Urea forms an ideal solution. Urea forms an ideal solution in water. Determine the vapor pressure of an aqueous solution containing 10% by mass of urea at 40 degrees Celsius, and it is given vapor pressure of water at 40 degrees C is 55.3 millimeter Hg. Okay, so urea forms an ideal solution. That means it will obey a Raoult's law in water. Determine the vapor pressure of a aqueous solution containing 10% mass of the urea at 40 degrees Celsius. So let's see the solution. So here it is given that P naught is 55.3 millimeter Hg and the solution is 10% by mass of urea. That means 10 gram of urea are present in 100 gram solution, right? So 10% by mass, it will mean 10 gram of urea present in 100 gram of solution. Okay, so we got mass of urea as 10 gram and mass of solution is 100 gram. So mass of solvent, that is water, mass of water would be 100 minus 10, that is 90 gram. Okay, so moles of urea is number of weight by molecular weight. So molecular weight of urea is 60. So you will get it as 0.167 and moles of water in solution is weight is 90 gram, molecular weight is 18. So it will be 5. So let us say mole fraction of urea, that is urea is our solute. So chi solute is number of moles of urea by total number of moles, that is 0.167 by 0.167 plus 5. You will get it as 0.032. Now you know, according to Raoult's law, P naught minus P by P naught is your chi solute, mole fraction of solute. We have derived this relation. Please see that relation. So if we substitute, P naught is given as 55.3, P is not given. This is 55.3, and chi solute, that is urea, we have found out 0.032. So after calculating, you will get it as 53.5 millimeter of Hg. Okay, so hence vapor pressure of the given solution at 40 degrees Celsius is 53.5 millimeter of Hg. So if you notice one thing, that if your theory is clear and you know all the formula and logic, the question will be very easy. Okay, there will be no question which will come out of your syllabus. The only thing that can happen, that it can be conceptual. Okay, now we are moving forward to our next most important topic, that is colligative properties. Okay, colligative properties and relative molecular masses, of non-volatile substance. Let us see. This colligative property is very important. So colligative properties are related to the number of solute and solvent particles present in a solution and do not depend upon the nature of the solute. Right? We have seen the definition. So the properties of solutions which depend upon the number of solute particles, that is molecules or ions, present in a definite amount of solvent but not on the chemical nature of solute, are called colligative properties. So let us write the definition. The properties of solutions which depend upon the number of solute particles. It can be molecules, it can be ions, present in a definite amount of solvent, but not on the chemical nature, of solute, are called colligative properties. So the particles of solutions which depend upon the number of solute particles present in a definite amount of solvent but not on the chemical nature of the solute are called colligative properties. That means it only depends on the number of solute particles, not on the chemical nature of solute. These are known as colligative properties. And there are few important colligative properties we will discuss in this course, that is relative lowering of vapor pressure, the elevation of boiling point, the depression of freezing point, and osmotic pressure. So these are some important colligative properties. Relative lowering of vapor pressure, the elevation of boiling point, the depression of freezing point, depression of freezing point, and osmotic pressure and osmotic pressure. So there is no exam without this. There will be a minimum of one question or two questions from these colligative properties. Okay, and so be careful and learn it very carefully. Okay, so relative lowering of vapor pressure. So our first is relative lowering of vapor pressure. Let's discuss about this. So we have already seen that the vapor pressure of a volatile solvent gets lowered when a non-volatile solute is dissolved in it, right? So if P naught represents the vapor pressure of a pure solvent, let us say P naught is the vapor pressure of a pure solvent, and P is the vapor pressure of solution. Then we have seen that lowering of, from Raoult's law we have derived this, right? Lowering of vapor pressure is P naught minus P. And we have also seen relative lowering of vapor pressure is given by P naught minus P by P naught. The relative lowering of vapor pressure as well as the lowering of vapor pressure are colligative properties. This lowering of vapor pressure and relative lowering of vapor pressure are colligative properties. And it depends upon the number of solute particles but not upon its nature. Okay, so we have seen from Raoult's law that this relative lowering of vapor pressure P naught minus P by P naught is your chi solute, right? So from this equation it is clear that the relative lowering of vapor pressure of a solution depends only upon the mole fraction of solute, right, and is independent of nature. Since mole fraction represents the number of moles of solute dissolved in a definite number of moles of solvent, the relative lowering in vapor pressure is a colligative property. Okay, because it only depends on number, right? P naught minus P by P naught is chi. Chi is number of moles. So it's a number, that's why it is a colligative property. Okay. Now If we see determination of relative molecular mass of a solute on the basis of relative lowering of vapor pressure. So let us see determination of relative molecular mass of a solute on the basis of on the basis of relative lowering of vapor pressure. So let us see this. See, we have just seen that according to Raoult's law, P naught minus P by P naught is chi solute. P naught is vapor pressure of pure solvent. P is vapor pressure of solution, and chi solute is the mole fraction of solute in solution. Okay. Now this relation can be used to determine the molecular mass of the solute provided relative lowering of vapor pressure is known. So let us move forward and elaborate the explanation. If the solution contains n moles of solute dissolved in capital N moles of solvent, so we can say that chi solute is n by n plus capital N. Okay, so we can write this equation as P naught minus P by P naught is your n by n plus capital N. Now let us say W is mass of solute, capital W is mass of solvent, capital M is molecular mass of solvent, molecular mass of solvent, and capital M prime is molecular mass of solute. So we can say number of moles of solute is weight by molecular weight, and number of moles of solvent is weight by molecular weight. So if we put it in this equation, we will get P naught minus P by P naught is W small w by M prime by small w by M prime plus capital W by capital M. Okay. So if we know the relative lowering of vapor pressure and the values small w, capital W and capital M, the molecular mass M prime, okay, of the solute can be calculated. Now if we assume that for a very dilute solution, for a very dilute solution, this equation can be rectified as or simplified as. Now see, if the solution is very dilute, the amount of solute is much less, right, as compared to that of solvent. So if n, the number of moles of solute, is less than capital N, number of moles of solvent, then what we can do is we can write capital N plus small n. We can ignore small n. This can be written as capital N. So this equation will reduce this equation. Chi solute is n by n plus n. This solution equation will reduce to P naught minus P by P naught will reduce to n by capital N, right? So we can say P naught minus P by P naught is weight by molecular weight of solute and weight by molecular weight of solvent, right? So this is the basics. This is the basic formula for dilute solution. Remember this, it's very important. We'll apply this in sums. Okay, you can substitute this, or you can remember this also. P naught minus P by P naught. If you simplify this, you will get small w capital M by capital W capital M prime. Or you can come from this. Okay. So from this you can calculate capital M prime if you know all the values. So let us see some question. Let us see some question based on this formula so that the application of this formula will be more clear. So the question is, a current of dry air is passed through a bulb containing 5 gram of a solute in 100 gram of water, and then through water alone. Water alone. The loss in the weight, the loss in the weight of the solution and pure water were respectively 0.78 gram and 0.02 gram. Calculate number A, relative lowering of vapor pressure, and B, molecular weight of solute. So let us see the solution of this question. Current of dry air is passed through a bulb containing 5 gram of solute in 100 gram of water, and then through water alone. The loss in the weight of the solution and pure water were respectively this and this. Calculate relative loading of vapor pressure and molecular weight of solute. So it's given that loss in the weight of solution, loss in the weight of solution is 0.78 gram, and loss is given that, right? Solute. Loss in the weight of solution and pure water. So it's the loss in the solution. And loss in the weight of solvent. Here solvent is water, right? Is also given 0.02 gram. Okay. So for this, you have to know one formula. I have skipped this formula. I am writing it here. P naught minus P. Let's write this formula. P naught minus P by P naught is loss in the mass of solvent bulb by loss in the mass of solution bulb plus loss in the mass of solvent bulb. Loss in the mass of solvent bulb. Remember this. By this formula, you can calculate this. You don't have to, we don't need the explanation here, because otherwise this lecture will be too lengthy. So see here, everything is given. Loss in the weight of solvent bulb by loss in the mass of solvent bulb plus loss in the mass of solution bulb plus loss in the mass of solvent bulb. So every information is given, and so you can put the values and can calculate the relative loading of vapor pressure. So let us put the values. If we put the values, we will get P naught minus P by P naught is 0.02 by 0.78 plus 0.02. We will get it as 0.025. Okay. So relative lowering of vapor pressure is 0.025. Now see, in the second part, they are asking about molecular weight of solute, right? So let us see the molecular weight of solute. See, it is given weight of solute is 5 gram. Okay, yeah, it's given that 5 gram is the weight of solute and 100 gram is the solvent. So weight of solute is 5 gram. This is our small w. Weight of solvent capital W is given 100 gram, and we know molecular weight of solvent, so in this case water, is 18, right? Now if we take that the solution is dilute, then we have seen the last formula as P naught minus P by P naught as small w capital M by capital W capital M prime. So this value we have calculated just now, 0.025. That's equals to weight of solute, that is 5 gram. This capital M is weight of solvent, that is capital 18, by this is the weight of solvent, that is 100, and we have to calculate from this capital M prime. So if you calculate, you will get capital M prime as 36. Okay. Now we will learn about elevation of boiling point. So our topic is elevation of boiling point. Okay, इसको एक शॉर्ट नाम भी देते हैं एब्लियोस्कोपी, ABU एब्लियोस्कोपी. Okay, so see, a liquid has a definite vapor pressure at a definite temperature. When the temperature is raised, its vapor pressure also increases, because more number of particles will evaporate and it will create more pressure on the surface of the liquid. If the heating is continued, a stage comes when the vapor pressure of the liquid becomes equal to the atmospheric pressure. At this stage, the liquid is said to be boiling, and the corresponding temperature is referred to as boiling point of the liquid. Thus, the boiling point of a liquid can be defined as, so let me write the definition first. The temperature at which the equilibrium vapor pressure of a liquid becomes equal to the atmospheric pressure is called boiling point of that liquid. ओके, सो यहाँ पे ये चीज याद रखना कि जब तुम टेम्परेचर बढ़ाते जाओगे, एक स्टेज ऐसा आएगा जहाँ पे बॉइलिंग पॉइंट और टेम्परेचर, एटमॉस्फेरिक प्रेशर सेम हो जाएगा. उसी पॉइंट को हम लोग बॉइलिंग पॉइंट बोलेंगे. ठीक है, जैसे देखो, अगर एग्जांपल ले, बॉइलिंग पॉइंट ऑफ ए प्योर वाटर हम लोग को पता है 373 केल्विन, दैट इज 100 डिग्री सेल्सियस. इट मीन्स दैट at 373 Kelvin, the vapor pressure of pure water would be equal to the atmospheric pressure. So if we take this example, boiling point of water is 373 Kelvin. Okay, it means at 373 Kelvin, the vapor pressure of pure water, vapor pressure of pure water would be equal to atmospheric pressure. Okay, atmospheric pressure. Now, when a solute is dissolved in a solvent, its boiling point is raised. So, next important point is when a solute is dissolved in a solvent, its boiling point is raised. Okay, the increase in boiling point thus obtained is referred to as elevation of boiling point. Okay, the increase in boiling point is referred to as elevation of boiling point. It's a qualitative property. Okay, now we'll see elevation of boiling point. See, we have seen that the vapor pressure of a solvent gets lowered when a non-volatile solute is dissolved in it, right? Because it will stop the evaporation of some particles below uh, those molecules, right? So, in other words, we can say that the vapor pressure of a solution is always less than that of a pure solvent. Therefore, the temperature at which the vapor pressure of a solution equals to the atmospheric pressure is higher than the temperature at which the vapor pressure of the pure solvent equals to the atmospheric pressure. And the boiling point of a solution would be higher than that of the pure solvent. Okay. So, the addition of a solute to a pure solvent increases the boiling point. Okay. So, when we add a solute, it will increase the boiling point. The increase in the boiling point of a solvent on addition of a solute to it is called elevation of boiling point of solvent for that solvent. Now, if we want to understand this by a graphical representation, so let's draw the graph first. So let us say we have the graph looks like this. Okay. I have to redraw it. This is our graph. It should go in this manner. Now let us say we have a point here, that is E point, and this pressure is P2, this pressure is P1, this point is D point, and this pressure is P0. This point is A, this point is B, and this point is C. Now let us draw the horizontal perpendicular graph, perpendicular line. Now see, in y-axis we have vapor pressure, and in x-axis we have temperature in Kelvin. Let us say this is your Tb, this is your T1, and this is your T2. Now let us say this is your 1 atmosphere, 1 atm. This is pure solvent. This line is your solution 1. This line is your solution 2. This gap is your delta Tb1, and this gap is your delta Tb2. Okay. Now if we see this graph, in this graph the variation of vapor pressure with temperature for pure solvent, this is your pure solvent graph, this is your solution 1, this is your solution 2. Okay. In this graph we can see that the variation of vapor pressure with temperature for pure solvent. See, this graph is for pure solvent. Solution 1 and solution 2 has a higher concentration as compared to that of solution 1, right? Now it is clear that pure solvent boils at temperature Tb. This is your temperature Tb. Okay, so pure solvent boils at temperature Tb, that is, now it is saturated and it's equal to 1 atm, atmospheric pressure. Okay, corresponding to point A, when is vapor pressure equals to the atmospheric pressure. Solution 1 boils at temperature T1, the solution boils at temperature T1, and solution 2 boils at temperature T2. Okay, now from the graph it is clear that T1, this T1, see the right hand side, T1 is greater than Tb, right? In this graph T1 is greater than Tb. Thus the boiling point of solution 1, this boiling point temperature T1, is higher than that of pure solvent Tb. Okay, the difference delta Tb1 between the two boiling points T1 and Tb is the elevation of boiling point. So this is your elevation of boiling point for solution 1. the boiling point of solution 2 is still higher than as the solution is more concentrated. So this solution is more concentrated. It boils at temperature T2 as it is clear from the graph. It boils at temperature T2 and it is higher than Tb. Okay. Now the difference delta Tb2 between temperature T2 and Tb is the elevation of boiling point for solution 2. This is the elevation of boiling point for solution 2. So we can conclude that elevation of boiling point for solution 1 is T1 minus Tb, that is delta Tb1, and elevation of boiling point for solution 2 is T2 minus Tb, that is delta Tb2. So it's very easy, right? Now let us see expression for elevation of boiling point. Expression for elevation of boiling point. Now see, if the curve BD, this curve BD and CE, this curve, are assumed to be straight line. It's almost straight line. If we assume that BD and CE are straight lines, then triangle ABD, this triangle is a straight line we have assumed, and ACE, this triangle ACE are similar triangle, right? So we can say triangle ABD are similar to triangle ACE. These are similar triangles. Now we know that for similar triangle AB by AC, that should be AD by AE. See, we have to go in order. AB by AC. So this line AB by AC is equal to AD. If we have taken AD, then we have to take AE. So AD divided by AE. We can say this, right, from geometry. Now, what is this AB? AB is T1 minus TB. This T1 minus TB, T1 minus TB. And what is this AC? AC is T2 minus TB, T2 minus TB. What is this AD? AD is P0 minus P1, P0 minus P1. And what is this AE? P0 minus P2, P0 minus P2. So this is our expression. Okay. Now we already know this notation. P naught is vapor pressure of pure solvent at boiling point Pb, which is equal to 1 atm. P1 is vapor pressure of solution 1 at temperature Pb, and P2 is vapor pressure of solution 2 at temperature Pb. So we can write this expression as delta Tb1 by delta Tb2, that is equals to delta P1 minus by delta P2. Okay, you can remember this expression. Now this delta Tb1 is your elevation of boiling point of solution 1, elevation of boiling point of solution 1. This delta Tb2 is your elevation of boiling point for solution 2. This delta P1 is lowering in vapor pressure for solution 1, and this delta P2 is your lowering in vapor pressure for solution 2. So we can simply say that delta Tb is directly proportional to delta P, because delta P Tb1 and delta P1 is in the numerator and delta Tb2 and delta P2 the denominator. So you can simply say delta Tb is directly proportional to delta P. So elevation of boiling point is directly proportional to lowering in vapor pressure. Okay, so we can make the statement elevation of boiling point is directly proportional to the lowering in vapor pressure. Now see, we know from Raoult's law that for a dilute solution P naught minus P by P naught is W into M by capital W into M prime. We have derived this relation, right? So we can say delta P by P naught is W into M by capital W into M prime. So delta P is P naught into capital M by small w by capital W into M prime. See, this P naught and capital M are constant for a particular solvent, right? This term is constant for particular solvent. So we can write delta P is proportional to W by capital W into M prime. Now if we compare this with the equation just we have seen, we have seen that delta PB is proportional to delta P. Now we got delta P is proportional to W by small w by capital W into M prime. So we can say delta TB is proportional to W by capital W into M prime. Okay. Now if we take the mass of solvent, let mass of solvent, that is capital W is 1 kg. Okay. If we take capital W as 1 kg, then this term W by capital W into M prime, which is this term will represent molarity M of solution. So we can say delta PB is directly proportional to molarity. Molality, sorry, this is not molarity, this is mass in kg, so this would be molality. Molality, small m. So delta TB is directly proportional to small m. And if we remove the constant, we will get delta TB is KB into small m. Okay. So this expression represents a relationship between elevation of boiling point and molality of the solution. Now here Kb is a constant. This constant is known as molar elevation constant. Molar elevation constant or ebullioscopic constant. Ebullioscopic constant. So we can define ebullioscopic constant as if molality is 1, then this ebullioscopic constant is equals to elevation of boiling point, right? So molar elevation constant is may be defined as equal to elevation point when the molality of the solution is 1. Okay. Since a molar solution consists of 1 mole of substance dissolved in 1000 gram or 1 kg of the solvent, the molar constant can be defined as molar elevation constant is the elevation of boiling point produced on dissolving 1 mole of a substance in 1000 kg of solvent. So let me write it here. It's very important. the molar elevation constant is the elevation of boiling point is the elevation of boiling point produced on dissolving 1 mole of a substance in 1000 gram or 1 kg of the solvent. Okay, did you get it? And if we talk about unit, then units of kb can be written as Kelvin per molar or degree Celsius per molar or Kelvin kg per mole. Okay, so these are the units. Now remember another equation. Molar elevation constant can be calculated from this relation mr pb square by 1000 into delta hv. Now we know this pb, this is boiling point of solvent. This delta hv, this delta hv is molar enthalpy of vaporization of solvent. This is molar enthalpy of vaporization of solvent. Okay. Now what is this? This is latent heat. This is latent heat of vaporization. Latent heat of vaporization for 1 mole of the solvent. And capital M is molecular mass of solvent, and capital R is gas constant. From this expression we can calculate the constant Kb. Now latent heat of vaporization per gram of the solvent is Lv, and that is related to Hv as the latent heat of vaporization per gram of the solvent. This is denoted as Lv, is related to Hb as Hb as Lv is delta Hv by m. So we can rewrite this expression as Tb is R Tb square by 1000 Lv. Okay. From this expression also we can calculate this Kb. Now see, if you remember this expression delta Tb proportional to molality, we can conclude some conclusions. The elevation of boiling point for a solution is directly proportional to the molality of the solution, as we know. This generalization directly infers that the elevation of boiling point is a colligative property, right? Because it depends upon the molality of solution, that is the number of moles of solute dissolved in a definite amount of solvent and not on the nature of solute. That's why it's a elevation of boiling point is a colligative property. Now in exam they can ask you show that elevation of boiling point is a colligative property. So from this equation, after coming to this equation, you have to say as I told you. Equimolar solutions of different non-volatile and non-electrolytic substances dissolved in the same solvent exhibit the same elevation of boiling point. Thus, the solutions of different non-volatile and non-electrolytic substances prepared in the same solvent and having the same molality will record the same elevation of boiling point. Okay, remember this. So we can conclude that the elevation of a boiling point, the elevation of a boiling point is a colligative property. And number two, equimolar, that means molality same होगा. Equimolar solutions of different non-volatile and non-electrolytic substances dissolved in the same solvent exhibit the same elevation of boiling point. Remember, this is very important point. Now if we want to find out relative molecular mass of the solute on the basis of elevation of boiling point, so we want to find out determination of relative determination of relative molecular mass of the solute on the basis of elevation of boiling point. Let us see the expression. See, the molecular mass of a solute dissolved in a particular solvent can be determined with the help of elevation of boiling point for the solution. Let us say W gram, this is small w, W gram of a solute are dissolved in capital W gram of a solvent, and molality is M. Now see, we know the definition of molality, that is number of moles of solute divided by mass of solvent in kg. Mass of solvent in kg. So number of moles of solute, that means weight by molecular weight, and mass of solvent in kg, that means we have to divide capital W by 1000. So molarity is 1000 multiplied by small w by capital W into M prime. Now here M prime is molecular mass of solute or molecular weight of solute. So it is molecular mass of solute. Now if we put this in the equation, delta Pb is Kb into M. If we put this in this equation, we will get delta Tb is Kb into 1000 into W by W into M prime. So from this you can calculate molecular mass, that is M prime is 1000 into Kb is 1000 into Kb into W by capital W into delta Tb. Okay. Now you can remember this equation. It will be helpful in solving sums. Now remember another equation. Sometimes this formula, capital M 100 into Kb prime into W by capital W into delta TB is also used for the calculation of molecular mass of solute. Okay, this is molecular mass of solute. This formula also can be used to calculate the molecular mass of solute. Now here Kb prime stands for molecular elevation constant. Molecular elevation constant. Okay, which is defined as the elevation of boiling point produced on dissolving 1 mole of substance in 100 gram of the solvent, and that Kb prime is given by R Tb square by 100 into Lb. Okay, now you already know what is Lb, on what is R, what is Tb. So remember these expressions. Now see, in this equation, the molecular mass of a non-volatile and non-electrolytic solute can be calculated, provided the elevation of boiling point and other values are known. And this equation, delta TB equals to Kb into M, is valid only for a non-electrolytic solute. If the solute dissociates into ions or associate to form polymer in the solution, the equation is not valid. Okay, remember these points. These are very important points. Now, let us see some question so that you would know how to use the equations we have discussed. So, let us see our first question. 10 grams of a non-volatile solute when dissolved in 100 grams of benzene raise its boiling point by 1 degree Celsius. What is the molecular mass of the solute? Kb for benzene is given as 2.53 Kelvin kg per mole. We already discussed about the units, right? So we talk about the solution. Kb is given 2.53 Kelvin kg per mole. W is given 10 gram, this small w, 10 gram. Capital W is given 100 gram, and delta TB is 1 degree. Now remember one thing, value of TB, the value of TB the value of delta TB is same on both Kelvin and Celsius scales. Okay, remember this is very important. Now, if we put in our equation, we have seen m prime is 1000 into kb into small w by capital W into delta TB. We have seen this equation. Put the values in it. 1000 into 2.53 into 10 by 100 into 1. Its value comes out to be 253 gram per mole. Okay. So these type of problems are actually very easy if you remember the formula and the logic behind that formula. Now let us see another question. A solution of 3.795 gram of sulfur in 100 gram of carbon disulfide boiling point is given. Boiling point is 46.30 degrees Celsius. Delta H vapor is given, vaporization is given 6400 calorie per mole. Boils at 46.66 degrees Celsius. What is the formula of sulfur molecule in the solution? So let's see the solution. It is given latent heat of vaporization. Latent heat of vaporization delta HV is given is 6400 calorie per mole. Boiling point of carbon disulfide is given. Boiling point of carbon disulfide TB is given 46.30 degrees Celsius. Converting it into Kelvin, it will be 319.3 Kelvin. Now we know molecular mass of carbon disulfide. Molecular mass of carbon disulfide is 12 for carbon and 64 for H2, 76. We know this relation. I have just told you. mR PB square by 1000 into delta HV. Right? That's why every formula is important. So don't ignore any single formula. This will be 76, the molecular mass of carbon disulfide, into gas constant R is 1.987. You can take it as 2 also. Pb is 319.3 square divided by 1000 into 6400. If you calculate, you will get it as 2.41. Now see, given that small w is 3.795, solute दे दिया है 3.795, solvent भी दे दिया है 100 ग्राम, weight, and capital W is 100 gram. So what would be delta TB? Delta TB would be 46.66 minus 46.30. It's given, right? Boils at 46.66. And 40 minus 46.30, it will be 0.36 degree. And we know this equation also. M prime is 1000 into kb into small w by capital W into delta TB. So it is 1000 into 2.41. We have calculated the value of kb. So 3.795 by 100 into 0.36. It would be 254.05. Right? Now see, we know atomic mass of sulfur 32, right? Atomic mass of sulfur is 32. So number of sulfur atom is 254.05 divided by 32. You will get it as 7.94, which is almost equals to 8. So formula for sulfur molecule is S8. Okay, in the solution, the formula for sulfur molecule is S8. That's how you have to calculate. Now let's move forward to our next colligative property. That is depression of freezing point. In short, it is known as cryoscopy. Cryoscopy. You see, cryoscopy. See, we know what is freezing point. The temperature at which the liquid and solid forms of substance can exist together in equilibrium is called the freezing point of that substance, right? Liquid और solid एक ही साथ रहेगा, एक ही साथ exist करेगा. At freezing point, the vapor pressure of the liquid, form of the substance is equal to that of its solid form. So remember this. At freezing point, the vapor pressure of the liquid form of the substance is equal to that of its solid form. Now, let us see a graph and then we'll discuss depression of freezing point. So, let us draw it. Again, the y-axis it is vapor pressure and the x-axis it is temperature in Kelvin. This point is your A point. Okay. So let us see. Let us say this is your P naught. This is your P1 and this is your P2. Let us say this point is C. This point is B. Let us draw a perpendicular to get the temperature. This is your point D. This is your point E. This portion is frozen solvent. Frozen solvent. This is liquid solvent. This is solution 1 and this is solution 2. Let us say this is T2, this is T1 and this is your freezing point TF. This gap is delta TF1. This gap is delta TF2. Okay. So when a solute is dissolved in a solvent, the freezing point of the solvent gets lowered. Okay. So let me write it here. When a solute is dissolved in a solvent, the freezing point of the solvent gets lowered. This lowering of freezing point is termed as depression of freezing point. Okay, this is your depression of freezing point. It is also a colligative property and depends upon the number of moles of solute dissolved in a definite amount of solvent. Now, let us elaborately explain this phenomena. So, a liquid, that is a solvent, freezes when its vapor pressure becomes equal to that of its own solid. Okay. So, a liquid, in this case solvent, freezes when its vapor pressure becomes equal to that of its own solid. Let us say ice and water. When a solute is dissolved in the solvent, the vapor pressure gets lowered. We already told this. Due to lowering of vapor pressure, the solution would freeze at a lower temperature as compared to the temperature at which pure solvent freezes. Thus, addition of a solute to a solvent decreases the freezing point of the solvent. The decrease in the freezing point of a solvent caused by the addition of a non-volatile solute to it is termed as depression of freezing point. Now, let us see by this graph. Here is a variation of vapor pressure with temperature for a pure solvent, solution 1 and solution 2. Solution 2, this solution 2 being more concentrated as compared to solution 1 at point A, the vapor pressure of the liquid solvent becomes equal to that of the frozen solvent. Okay, at this point, vapor pressure of liquid solvent is equal to frozen solvent. And the two phases exist in equilibrium. Therefore, point A corresponds to temperature Tf. This is your freezing point, Tf. Okay. The freezing point of a pure solvent, this is freezing point of a pure solvent, Tf. When a solution freezes, the solid that separate out is usually the pure solid solvent. Since the vapor pressure of a solution is less, it can be in equilibrium with the frozen solvent only when the vapor pressure of the frozen solvent is also less. This will happen at lower temperature. Okay, it will happen at lower temperature. The solid will freeze at a lower temperature than the one that at which pure solvent freezes. So it is clear from the graph that solution 1 is a solution 1. Solution 1 freezes at point B. There is a partial pressure and there is a freezing temperature T1, at which its vapor pressure becomes equal to that of frozen solvent at this point. Obviously, temperature T1 is less than Tf, right? We are going in the origin site. So less than Tf, the freezing point of pure solvent. This Tf is freezing point of pure solvent. Now the difference delta Tf1, this gap between the two freezing point Tf and T1 is the depression of freezing point for solution 1. And for solution 2, being more concentrated, the solution 2 is more concentrated, possesses a still lower vapor pressure. See it at T2. Its vapor pressure becomes equal to that of frozen solvent at point C, corresponding to temperature T2, which is still lower. The difference delta Tf2 between freezing point of pure solvent Tf and the freezing point of solution 2 T2 is the depression of freezing point of solution 2. So delta Tf2 is this gap. This is your delta Tf2. This whole gap is delta Tf2. So we can say depression of freezing point for solution 1 is Tf minus T1, that is delta Tf1, and depression of freezing point for solution 2 is Tf minus T2, that is delta Tf2. Now if we talk about expression, then if we talk about expression for depression of freezing point, okay, if we talk about expression for depression of freezing point, so to derive we have to go in the previous way as we have derived. Now here AB, this line we have to take it as a straight line. AC, this AC line. BD, this BD, and CE, this A or CE, okay, are assumed to be straight line. This is your straight line. Let us assume this as a straight line. This line, and this line are all straight lines, and this is a perpendicular, so it will be a straight line. So from this triangle ABD, this triangle ABD and ACE, we can conclude. So from triangle ABD and triangle ACE, these are similar triangle, right? Are similar triangle. These are similar triangle. Now for this we can say BD, ABD, not C, ABD. So BD by C, that should be equals to AD by AE. Order is important, right, in terms of ratios. So BD by CE, that is equals to AD by AE. Now what is this BD? BD is Tf minus T1. What is this CE? CE is Tf minus T2. What is this AD? AD is P0 minus P1. And what is this AE? AE is P0 minus P2. So let's put the values. So if we put the values, Tf minus T1 by Tf minus T2, that is equals to P0 minus P1 by P0 minus P2. Okay. Now here P0 is vapor pressure of liquid solvent, vapor pressure of liquid solvent at its freezing point. At its freezing point, TF. This P1, this P1 is P1 is vapor pressure of solution 1 at temperature T1. P2 is vapor pressure of solution 2 at T2. So we can write this expression as delta TF2 delta TF1 because TF minus T1 divided by delta TF2 is delta P1 by delta P2, right? So we can see that TF1 delta P1, TF2 delta P2 are in proportion. So we can say delta TF is proportional to delta P. Okay. So we can say in statement that depression of freezing point is directly proportional to lowering of vapor pressure. So you can say in statement depression of freezing point is directly proportional to the lowering of vapor pressure. So according to Raoult's law, we know according to Raoult's law, we know P naught minus P by P naught is small w capital M by capital W capital M prime. So we can write delta P by P naught is small w capital M by capital W capital M prime, right? So this delta P would be P naught into M multiplied by small w by capital W into capital M prime. Now this term is constant for a particular solvent. This is constant for particular solvent. So we can say that delta P is directly proportional to W by capital W into M prime. Now if you compare with this equation, you can put in place of delta P delta TF. So we can say delta TF is directly proportional to W by capital W into capital M prime. Now let us say if W, that is mass of solvent is 1 kg and W small w by capital W capital M prime represents the molality, right? This term represents molality m. So we can say delta Tf is directly proportional to molality, and if we omit proportionality, then we will get delta Tf is Kf into m. So this expression represents a relationship between the depression of freezing point and molality of the solution. Okay, and this Kf is a constant. This is known as molar depression constant. Molar depression constant or cryoscopic constant or cryoscopic constant. Okay, if you want to divide, if you take molality is 1, then Kf is delta Tf. So molar depression constant may be defined as equal to the depression of freezing point when the molality of the solution is unity. Okay, and since a molar solution, that is 1 molar solution, consists of 1 mole of a substance dissolved in 1000 gram or 1 kg of the solvent, so molar depression constant can also be defined as Kf can also be defined as the molar depression constant is the depression of freezing point produced on dissolving 1 mole of a substance in 1000 gram, that is 1 kg of the solvent. And if you talk about unit, so units of Kf will be, this is Kelvin per mole, degree Celsius per mole, or Kelvin kg per mole. Now this Kf can be calculated with the relation Kf is mR Tf square by 1000 into delta H fusion. Remember this expression also, it will be helpful in solving question. mR Tf square by 1000 into delta H fusion. Here Tf we know, freezing point of solvent, freezing point of solvent, delta H fusion is molar enthalpy of fusion of frozen solvent, and it can be defined as latent heat of fusion for 1 mole of frozen solvent. Capital M is molecular mass of solvent and R is gas constant. R is gas constant. Okay. And latent heat of fusion per gram of the solvent is related to as latent heat of fusion, latent heat of fusion per gram of the solvent LF is related to as LF is delta H fusion by M. Okay. And this Kf can also be written as R into Pf square by 1000 LF. Okay. So these are the formulas related to depression of freezing point. Now, if you see this relation delta Tf is Kf into M, on the basis of this we can conclude that the depression of freezing point of a solution is directly proportional to molality of the solution. That means depression of freezing point is a colligative property, right? Because it depends upon the molality of solution, that is number of moles of solute dissolved in a definite amount of solvent in kg. So this delta Tf is a colligative property, right? So we can say, wait a minute. So we can say that depression of freezing point, depression of freezing point is a colligative property. Is a colligative property. And number two conclusion we can make: equimolar solutions of different non-volatile and non-electrolytic substances dissolved in the same solvent would be same, exhibit the same depression of freezing point as we have discussed in the elevation of boiling point cases, right? It's same. Equimolar solutions of different non-volatile and non-electrolytic substances dissolved in the same solvent exhibit the same depression of freezing point. Same depression of freezing point. Okay, thus the solutions of different non-volatile and non-electrolytic substances prepared in the same solvent and having the same molality will show the same depression of freezing point. It's a very important point. Remember this. Now see, we have to determine. Our next topic is determination of relative molecular mass of a solute on the basis of depression of freezing point. Now see, we know that molality is number of moles of solute by mass of solvent in kg. So this is weight by molecular weight, number of moles is, and this is mass of solvent in kg, so capital W by 1000. So our molality becomes 1000 into W prime by capital W into capital M prime. And capital M prime is the molecular mass of solute. Okay. Now if we put this in this equation, delta TF KF into M, we put in that equation, we will get delta TF is KF into 1000 into W by capital W into M prime. So from this we can say that capital M prime is 1000 into KF into W by capital W into delta TF. Okay. The molecular mass of a non-volatile, non-electrolytic solute can be provided the depression of freezing point and other, if other values are known, so we can calculate M prime. Okay. Now remember one thing, that this expression is valid only for a non-electrolytic solute, valid for only valid for a non-electrolytic solute, valid only for a non-electrolytic solute. Remember this. You cannot use this formula if it is electrolytic. If the solute dissociates into ions or associate to form a polymer in the solution, the equation is not valid. Okay. Now let us see one question regarding this. So if we see, calculate the amount of ice that will separate out on cooling a solution, containing 50 gram. Okay, the page is hanging, containing 50 gram of ethylene glycol in 200 gram of water, in 200 gram of water, to minus 9.3 degrees Celsius. Okay, and it is given that Kf for water is 1.86 Kelvin kg per mole. Let's see the solution. The amount of ice, that means solvent. Okay, so in this case it's given that small w is 50 gram, capital W we have to calculate solvent, delta Tf freezing point is 0, ice freezing point is 0, minus of minus 9.3, that is 9.3 degree. Okay, Tb minus T1, and Kf is given 1.86 Kelvin kg per mole, and molecular mass of glycol, molecular mass of glycol, that is CH2OH dot CH2OH. Okay, this is the glycol formula, and if you put all the values, then you will get M prime as 62, oxygen 16, hydrogen 1, carbon 12, put and add, you will get 62. So let us put in the equation we have just learned. M prime is 1000 into Kf into W by capital W into delta Pf. Okay, so from this we can rearrange, and capital W is 1000 into Kf into small w by capital M prime into delta Tf. So put all the values, it is 1000, Kf is 1.86, small w is 50, M prime is 62, delta Tf is 9.3. Its value comes out to be 161.29 gram. Okay, now you have to calculate the amount of ice that will separate out on cooling. So mass of water separated as ice, we can say ethylene glycol in 200 gram of water. So 200 minus 161.29, that is 31.71 gram is the amount of ice separated from water. That's how you have to solve these questions. These questions are not difficult, but you have to remember the formula and the logic. So let's move forward to our next topic, which is osmotic pressure. So let us see our next topic, which is osmotic pressure. Osmotic pressure. Okay, See, the solute particles present in a solution behave almost in the same way as the molecules of a gas do. Similar to gases, solutions also exhibit the phenomena of diffusion. When a pure solvent is taken over a solution, the solute particles diffuse from the solution into the solvent. In fact, diffusion exhibit by solution is a bilateral process in which solute molecules move into the solvent, and at the same time the solvent molecules move into the solution. So let us see a diagram. So here let us say this is our pure solvent, and this is our solution. Okay. Now let us say the solute particles, the solvent molecules go into solution, and these solute particles go into solvent. So this is our solute molecules, and this is our solvent molecules. Okay. Now see, this process continues till the system becomes homogeneous. The diffusion of solute also takes place when two solutions of different concentrations are kept in direct contact. Thus, solution process a tendency to equalize concentration in all parts, and this tendency is responsible for the diffusion of solute. So let us write this. The tendency of a solution to equalize concentration in all its parts gives rise to another important phenomena, gives rise to another important phenomena known as osmosis. Okay, known as osmosis. Osmosis. The phenomena of osmosis is related to an important colligative property, that is osmotic pressure. Okay. Now let us see what is osmosis. Osmosis. So first point is natural and chemical semi permeable membrane. Okay. So it is a membrane which allows the passage of only solvent molecules, not of solute particle, is called semi permeable membrane. So let me write it here. It is very important. A membrane which allows the process of which allows the process of which allows the passage of, not the process, which allows the passage of only solvent molecules and not of solute particles is called a semi permeable membrane. Okay, vegetable membranes and animal membranes are the natural membranes of this type. Okay, and the semi permeable membrane can be prepared artificially also. Now another is chemical semi permeable membranes. Okay, so cellophane, freshly precipitated inorganic substances such as copper ferrocyanide, silicates of iron, cobalt, nickel are some example of artificial or chemical semi permeable membrane. The copper ferrocyanide membrane is prepared by electrolytically depositing a precipitate of copper ferrocyanide obtained by the combination of CO2 plus ion and ferrocyanide ion, that is FeCN6 all to the power 4 minus ions, in the pores present in the walls of a porous pot. So we don't need that, just remember the examples, that is cellophane, freshly prepared inorganic substances, that is copper ferrocyanide, silicates of iron, silicates of iron, cobalt, nickel. Okay, and if we talk about natural membrane, these are vegetable membranes, vegetable membranes and animal membranes and animal membranes. When the semi-permeable membrane is placed between a solution and a pure solvent, this case, if you place the membrane here between the solution and pure solvent, it is observed that the solvent flows from the region of pure solvent into solution. Okay. Now, if we talk about, let's see the diagram. So it will be very easy to understand. And let's say we have two diagrams. One is this, and another one is this. Now, in this diagram here we have pure solvent and solvent molecules is traveling in this direction, and we have, let us say, solution. Here we have solution, and let us say these are our solute molecules. These are our solute molecules. Now this is our semi-permeable membrane. Semi-permeable membrane, and this level of solution increases due to net flow of solvent. So you can say level of solution rises due to net flow of solvent. And in the another diagram, if we take dilute solution, this is our dilute solution. This is our semi-permeable membrane. And this is our concentrated solution. Concentrated solution. And here also level of concentrated solution rises due to net flow of solvent. Due to net flow of solvent. Here you can give some pure solvent. Some molecules came into this, and this is our solvent molecules. This is our solvent molecules, and this is our solute molecules. This is our solute molecules. This is our solute molecules. Okay. Now, if we see this diagram, let us say this is diagram A and this is diagram B. So the solvent flows from the region of pure solvent into solution. Okay, it flows from pure solvent to solution. Similarly, if a semi-permeable membrane is placed between two solutions of different concentration, here we can see it is a dilute solution, it's a concentrated solution. The solvent flows from dilute solution. The solvent always flows from dilute solution to the concentrated solution. Okay, in this diagram. In fact, the diffusion of solvent molecules through the semi-permeable membrane takes place in both the direction. Okay, it takes place in the both the directions. It will also go from solution to pure solvent, and it also goes from solution, concentrated solution to pure solvent. Dilute solution to pure solvent and concentrated solution to pure solvent. The solvent molecules travels in this manner. Solute particles do not pass through the membrane. In either of the diagram, we can see that solute particles do not travel through semi-permeable membrane. Here also solute particles do not travel, only solvent particles travel through semi-permeable membrane. Okay. So when a solvent is separated from a solution through a semi-permeable membrane, greater number of solvent molecules pass from solvent into the solution as compared to those which diffuse from solution to solvent. This number is less. This number is large. Hence, the net flow of solvent is from solvent to solution. Similarly, when a dilute solution is separated from a concentrated solution through a semi-permeable membrane, the net flow of solvent is from dilute solution to solvent solution, concentrated solution. Right here, see here solvent molecules which are there in concentrated solution are less, and it is going less number of solvent molecules from concentrated solution to dilute solution than dilute solution to concentrated solution. This flow of solvent through the semi-permeable membrane is spontaneous and is termed as osmosis. So osmos means push. It's a Greek word. Thus, we can define osmosis as the spontaneous flow of the solvent through a semi-permeable membrane from a pure solvent to a solution, or from a dilute solution to a concentrated solution. This is osmosis. The phenomena of osmosis can be explained with the X. Okay. So let us see this example by X. We take a egg. This is our egg. Let us say egg material lies here. This is our egg material, and this acts as semi-permeable membrane. Semi-permeable membrane, and this is your shell. Okay. If we put this in, if we put the egg in water and salt solution, let us see how it will behave. So we have put the egg in water. Actually, it will swell in water. It will be bigger. So this is our egg, and it swells. This is our original size, and this is our water. Let's say this is our water. So egg swells in water. That means size increases. And if we put this egg into solution of salt, then it will shrink. So let us say this is our original size, and it will shrink. Okay, so this is our original size, and this solution is the solution we have taken here is saturated salt solution. This is saturated salt solution, and here we will observe that egg will shrink in salt solution. Okay, now the phenomena of osmosis we can explain with the help of an egg. So in an egg, the membrane below the shell and around the egg material is this semi-permeable membrane. This is your semi-permeable membrane. The outer hard shell can be removed by putting the egg in dilute hydrochloric acid. If we remove the outer shell and putting it into dilute hydrochloric acid, after removing the hard shell, one egg is placed in distilled water, in this distilled water, and other egg is put into a saturated salt solution. We will see the egg placed in distilled water swells up, and while the egg placed in saturated salt solution will shrink. Okay. In this first case, when we put the egg into distilled water, that is water here is our solvent, right? So this water enters into egg material, that is solution. In this case, our egg material is solution. Okay, causing the egg to swell up, because we just have come to know that solvent molecules travel from pure solvent to solution. So here egg material is our solution. So water will travel into solution. That is solvent move into solution. And in the second case, the concentration of salt solution is higher than that egg material. Here concentration concentrated saturated salt concentrated saturated salt uh, concentration of saturated salt is less than the concentration of here the concentration of salt solution is higher than that of egg material. Sorry, it is higher than the egg material. It is greater than the egg material. Okay, so you can say uh, water from egg material, which is a dilute solution, right? There will be water in egg material, which will be a dilute solution in this case. So water in the egg material, water in egg, which is a dilute solution, to the salt solution, that is concentrated solution, right? This is your concentrated solution, causing the egg to shrink, because just now we have learned that when there will be a dilute solution and concentrated solution, the solvent particles from dilute solution will go into concentrated solution. So here the water that remains in the egg material are dilute solution, and in the outside we have concentrated solution of salt. So the solvent molecules, that is water particles, will move from dilute particles to concentrated solution. So that's why the egg will shrink. Okay, and now see, there is a difference between diffusion and osmosis. diffusion involves the free mixing of the solution without a semi-permeable membrane, but osmosis involves the use of a semi-permeable membrane. In diffusion, both solvent and solute molecules move directly into each other. Thus, diffusion is a bilateral process. In osmosis, only solvent molecules move through the semi-permeable membrane. The movement of solute particle is checked by the semi-permeable membrane. Okay. In diffusion, solute particles move from higher concentration to lower concentration, while the solvent molecules move from lower concentration to higher concentration. And in osmosis, the net flow of solvent molecules is from lower concentration to higher concentration. And diffusion is shown by solutions as well as by gases. And osmosis is shown by solutions only. Diffusion can neither be stopped nor can be reversed, but osmosis can be stopped or reversed by applying external pressure on the solution having a higher concentration. So these are the some differences between diffusion and osmosis. So I think you got the point. If you want to write, please pause and listen again and write the difference, because it may come in your exam. Now our next topic is osmotic pressure. Osmotic pressure. So let's see what is osmotic pressure. See, just now we have seen that osmosis involves a net flow of solvent from solvent to solution, or from a dilute solution to a concentrated solution through a semi-permeable membrane. The flow of solvent is spontaneous but does not continue indefinitely. When a solvent is separated from a solution through a semi-permeable membrane, or a dilute solution is separated from a concentrated solution, the flow of solvent stops after a certain time. That is, the phenomena of osmosis stops. This enables us to define and measure the osmotic pressure. Let us say a concentrated aqueous solution is taken in a porous pot with copper ferrocyanide membrane, that is acting as semi-permeable membrane deposited in its walls. Now, if we want to see the osmotic pressure, let us first draw a diagram. Okay, let us see the diagram first. Let us say we have, because realizing this is very important. This is our final level. Final level. Let us say this is our initial level, and this difference is due to column exerting hydrostatic pressure. This difference is due to column exerting hydrostatic pressure. This is our solution, and let us say this is our solvent. This is our solvent. Okay. Now we will need another diagram. Let me draw it here. Then I will explain. Once you have realized anything pictorially, then it will be very easy for you to remember for rest of your life. So that's why the video is going lengthy, but I think once you have given time, you will never forget this chapter. This is our piston, and it is giving external pressure. External pressure. This is our solution. Let us say this is our solution, and this is our solvent. This is our solvent, and it's a glass tube. It's a glass tube, and this is our semi-permeable membrane. Okay. Now let us see in this diagram. In the first diagram, this is B diagram. In the first diagram, the pot is now immersed in distilled water. Okay, in the solvent, this pot is immersed in the distilled water. Since solution has been separated from a solvent through a semi-permeable membrane, okay, this is separated by a semi-permeable membrane. Through a semi-permeable membrane, the osmosis takes place and water from the outer vessel enters into the solution. Okay, this water will enter into the solution kept in the porous pot. So this is our porous pot. This causes the level of liquid in long glass tube to rise. Okay, it will rise. Now, if the apparatus is kept as such for a few days, the level of the liquid in the long glass tube, this level in the long glass tube of the liquid becomes stationary and attains a definite maximum value. This indicates that osmosis is no longer taking place and the net flow of water into the solution is stopped. This is possible only when the number of water molecules flowing from water to solution is the same as the number of water molecules flowing from the solution into water. Number of water molecules flowing from solvent to solution is equals to number of water molecules flowing from solution to solvent. This is possible only when the number of water molecules flowing from water to solution is same as the number of water molecules flowing from solution to water. The state of equilibrium is attained. At this stage, the hydrostatic pressure of the liquid column, is in the long glass tube counterbalances the driving forces for the occurrence of the phenomena of osmosis. That is, osmotic pressure. This will drive the osmotic pressure. Hence, osmotic pressure may be defined as a solution at a particular temperature may be defined as the hydrostatic pressure which builds up when the solution is separated from the solvent by a semi-permeable membrane uh, and which is just sufficient to stop the phenomena of osmosis. Now, this osmotic pressure may also be defined by this diagram. In this diagram, the apparatus consists of a chamber divided into two compartments by a semi-permeable membrane. One compartment is filled with solvent, and the other with a one compartment is with solvent and another with solution. Okay, prepared in the same solvent. The solution chamber is fitted with a movable piston. There is a movable piston, while the solvent chamber with a glass tube. Solvent has a chamber of glass tube and it has a piston. The driving force for the occurrence of osmosis is actually the difference in the vapor pressure of solvent and solution. Since the vapor pressure of solution is less than that of solvent, the escaping tendency of the solvent from the solution is less as compared to that from the pure solvent. Therefore, by applying an external pressure on the solution, the escaping tendency of the solvent from the solution may be made equal to that of solvent from the pure solvent, and the phenomena of osmosis can be checked. In the absence of external pressure, if external pressure is absent, osmosis will take place. In the absence of external pressure, osmosis will take place and the liquid level will fall in the glass. In the absence of external pressure, this liquid level in the glass will fall. Okay. Now, sufficient external pressure is applied. On the solution with the help of a piston to arrest the movement of liquid in the glass tube. When the liquid level in the glass tube becomes steady, if this liquid level is steady, there is no osmosis and the external pressure applied on the solution is equal to osmotic pressure of the solution. Hence, osmotic pressure can also be defined as the external pressure which should be applied to the solution in order to stop the phenomena of osmosis. That is to stop the flow of solvent into solution. When the two are separated by a semi-permeable membrane. Okay. Now, there is another term which is called reverse osmosis. Reverse osmosis. This is also important with respect to our examination. When the pressure applied on the solution is greater than the osmotic pressure of the solution, the solvent starts flowing from the solution into the solvent through the semi-permeable membrane, and this phenomenon is known as reverse osmosis. So this is very important. Remember the definition because it will come into your exam. When the pressure applied on the solution is greater than the osmotic pressure, of the solution the solvent starts flowing the solvent starts flowing from solution into the solvent through the semi-permeable membrane. Through the semi-permeable membrane. Okay, this phenomena is known as osmotic pressure. So, what does just happen? If you apply the pressure on the solution and which is greater than the osmotic pressure, you see here osmotic pressure stops when solvent molecule stops flowing into solution. Okay, the osmotic pressure is equal to the external piston pressure. At that moment, the solvent molecule stops flowing from solvent to solution. But here, when pressure applied on the solution is greater than the osmotic pressure of the solution, the solvent starts flowing from solution into the solvent. The solvent molecule will start flowing from solution to solvent, okay, through a semi-permeable membrane, and this phenomena is known as reverse osmosis. Okay. Now, how do we distillate seawater? Let us see this. Reverse osmosis. Reverse osmosis and water purification. Water purification. See, osmosis is a spontaneous process, right? And involves the flow of the solvent from a dilute solution to a more concentrated solution. We know this. When the two are separated by a semi-permeable membrane. This natural process, when reversed by applying a pressure greater than the osmotic pressure on the more concentrated solution, is called reverse osmosis. Just now we have learned what is reverse osmosis. When a pressure greater than the osmotic pressure is applied on the more concentrated solution, the solvent is forced to move from the more concentrated solution to the dilute solution through a semi-permeable membrane. This is the phenomena of reverse osmosis, and this phenomena of osmosis and reverse osmosis we can learn by these diagrams. So, if we see that, let us see the diagram. Let us say this is our semi-permeable membrane. This is our semi-permeable membrane. This is our dilute solution. This is our dilute solution. And this is our concentrated solution. And here net flow of solvent is in this direction. Net flow of solvent. Okay. Now this is our osmosis, right? This is our osmosis. There is no doubt. Now what is reverse osmosis? We have to apply external pressure in the concentrated side, right? We have seen the definition. Now if we see reverse osmosis, we have to apply external pressure. Let us say this is our semi-permeable membrane. Semi-permeable membrane. This is our dilute solution. Here it will be higher because reverse osmosis will happen here. This is our dilute solution. This is our concentrated solution. Concentrated solution, and net flow will from concentrated solution to dilute solution if you apply external pressure. This is pressure. You are applying external pressure. So this is your net flow of solvent. Okay. This is the phenomena of reverse osmosis. Reverse osmosis. Now if you want to apply this reverse osmosis phenomena in seawater, so let us see how can we apply this. Let us say this is our semi-permeable membrane. Let us say this is our seawater, which is concentrated, right? And this is our fresh water. And you have a mechanism to keep the fresh water out of this system. Okay. That's how reverse osmosis will happen. This is distillation of seawater. Now let us see the phenomena of reverse osmosis had been found very useful for the distillation or purification of uh, brackish or seawater. So brackish water or seawater contains many dissolved salts and is more concentrated as compared to the fresh water. Therefore, if seawater is kept in contact with fresh water through a semi-permeable membrane and a pressure of the order of 15 to 40 kg per centimeter cube, this is 15 to 40 kg per centimeter square, is applied on the seawater, reverse osmosis will take place. and water, that is solvent, will be forced to flow from seawater to fresh water, leaving behind the dissolved salt. The distillation of brackish water or seawater is carried out in a reverse osmosis cell. In this cell, water to be desalined is separated from fresh water through a semi-permeable membrane made of very thin films of cellulose acetate. Okay, this is made of cellulose acetate affixed to either side of the perforated plate or tube. Okay, and in today's, if we see, superior membranes made of polymethacrylate and polyamide polymers have been introduced, and a pressure of 15 to 40 kg per centimeter square is applied to the seawater, and reverse osmosis will take place and fresh water is obtained. So it's a very simple phenomena. See, that's how the thing works. If you know physics, if you know science, you can apply a little concept to make the revolution. And if you remember, recently in 2018 or 19 maybe, Israel has gifted a machine uh, to convert seawater into fresh water instantly. I think it takes 10 to 15 minutes. Okay. And now we will see osmotic laws of osmotic pressure, laws of osmotic pressure, and Van 't Hoff factor and Van 't Hoff's factor, Van 't Hoff's equation. Let's say this. What are the laws here? See, Van 't Hoff in 1877 established that the solute particles present in a solution behaves exactly like the molecules of a gas, and the osmotic pressure of a dilute solution is equal to the pressure which the solute would exert if it were a gas at the same temperature and occupying the same volume as that of the solution. Okay, so is very important. I am repeating again. If you want to write, you can write. The solute particles present in a solution behaves exactly like the molecules of a gas, and the osmotic pressure of a dilute solution is equal to the pressure which the solute would exert if it were a gas at the same temperature and occupying the same volume as that of the solution. We also found that the ordinary laws obeyed by gases are also obeyed by dilute solution. So the ordinary gas laws, when applied to solutions, are referred to as laws of osmotic pressure. Okay, and these are as follows. First one is Boyle-Van 't Hoff law. Boyle-Van 't Hoff Van 't Hoff law. So according to this law, the osmotic pressure, the osmotic pressure of a dilute solution is directly proportional to its concentration. provided temperature remains constant. Okay. So osmotic pressure of a dilute solution is directly proportional to its concentration, provided temperature remains constant. So let pi be the osmotic pressure, be the osmotic pressure, and C is the concentration, concentration, concentration of a dilute solution, of a dilute solution. So according to this law, pi should be directly proportional to C. And remember, temperature should be constant. Now see, if concentration of solution is expressed in moles per liter and V is the volume containing 1 mole of the solute, then we can say C is 1 by V, right? So in that case, this equation we can write it as pi is proportional to 1 by V, provided T is constant. Okay, and this relationship, this relationship is similar to the Boyle's law for gases, right? And is known as Boyle-Van't law, because we know PV equals to constant, right? So here we got pi V equals to constant. So number 2 is Charles Van't Charles Van't law. So according to this law, the osmotic pressure of a dilute solution is directly proportional to the absolute temperature if concentration of the solution is kept constant. So mathematically we can write pi is the osmotic pressure, that is directly proportional to T. Okay. So if concentration of the solution is constant, so here concentration is constant. Remember this. And this relation is similar to Charles' law for gas, and it is known as Charles Van't law. Now next is our Avogadro Van't law. So according to this law, equal volumes of solutions contain equal number of equal number of moles or molecules of solute provided their osmotic pressure and temperature are the same. So this statement is similar to Avogadro's law. That's why it is Avogadro-Van 't Hoff law. See, we have already seen that pi is proportional to 1 by V at constant temperature, and pi is proportional to T when concentration is constant. This is Charles Van 't Hoff, this is Boyle's Van 't Hoff, right? So combining these two, we can write pi proportional to T by V. If we omit proportionality, then it is pi equals to S into T by V. So we can say pi V equals to ST. S is a constant and it is known as solution constant. So S is solution constant. Okay. Van 't Hoff showed that the value of solution constant is equal to that of the gas constant R. So according to Van 't Hoff, S is equals to R. So we can write pi V equals to RT. And this equation is similar to gas law, right? And is known as Van 't Hoff equation. Van 't Hoff equation. For n moles of solute dissolved in V liters of solution, this Van 't Hoff equation would be pi V equals to nRT. Okay. See, osmotic pressure is a colligative property, right? Osmotic pressure is a colligative property. So we can say pi V, we can say pi is equals to n by V RT. If temperature is constant, we can say R is also constant. So if we take, if temperature is constant and R is already a constant, so we can say pi is proportional to n by V, right? So the osmotic pressure of a solution depends upon the number of moles of solute dissolved in a definite volume of solution. That's all, right? And it does not depend upon the nature of solute. Hence, osmotic pressure is a colligative property. So we can conclude that osmotic pressure is a colligative property. Osmotic pressure is a colligative property. Now our next topic is determination of relative molecular mass. Determination of relative molecular mass of a solute on the basis of osmotic pressure. On the basis of osmotic pressure. Okay. So let W grams of a solute are dissolved in V liters of a solution, and M prime is the molecular mass. M prime is the molecular mass of the solute. So we can say number of moles is weight by molecular weight, and if we put in this equation Pv equals to pi V equals to nRT, if we put in this equation, we will see pi V is W by M prime into RT. So from this M prime would be WRT by pi V. Okay, remember this equation, or you can come from basics also. So from this you can calculate the molecular mass of solute. Okay, provided the osmotic pressure pi of the solution, mass W of the solute particles in V liters of the solution, and temperature T are known. The value of R, here value of R you have to take it as 0.0821 liter atmosphere per Kelvin per mole. Okay, remember this. Remember this. You have to apply this value. Okay, and pi is expressed in atmosphere, and volume is in liter, and T is in Kelvin. Now see, osmotic pressure determination is the most suitable method for the determination of molecular mass of proteins, polymers, and other macromolecules, because there are some reasons. Number one reason is biomolecules like proteins are not stable and they break down at high temperatures. Therefore, elevation in boiling point is not appropriate for the determination of molecular mass of biomolecules, but osmotic pressure can be measured at room temperature. Number two is, as the molecular masses of biomolecules are very high, the change in temperature for their solutions becomes very small, and it becomes difficult to measure them accurately, but osmotic pressure of such solutions is of the order of 10 to the power minus 3 atm and can be determined easily. So this method is very important. Now, if we move to our next topic, it will be isotonic, hypertonic, and hypotonic solutions. So let us see one by one. So what is isotonic solution? Number one is remember this will come in your exam. Isotonic solutions. When two solutions are separated by a semi-permeable membrane and no osmosis occurs, that is, there is no net flow of water on either side through the membrane, the solutions are said to be isotonic solution. So let me write the definitions because it's very important. When two solutions are separated by a semi permeable membrane and no osmosis occurs, that is, there is no net flow of water on either side through the membrane through the membrane, the solutions are said to be isotonic solution. Isotonic solution. Okay. If the membrane is perfectly semi-permeable, the two solutions possess the same osmotic pressure and are also referred to as isoosmotic solution. So in that case, let us see the mathematical expression. Let us consider two solutions designed as solution 1 and solution 2 at temperature T. Suppose solution 1 consists of N1 moles of solute dissolved in V1 liters and solution 2 contains N2 moles of solute dissolved in V2 liters. Okay. Now if the two solutions are isotonic, they would possess the same osmotic pressure according to the definition, right? So let the osmotic pressure of each solution be equal to pi. Okay. So according to Van 't Hoff equation, we can say for solution 1, pi V1 is N1 RT, and for solution 2, pi V2 is N2 RT. And if we divide this equation, both of the equations, we will get V1 by V2 is N1 by N2. Okay, or we can say N1 by V1 is N2 by V2. Remember this equation. So here N by V represents molar concentration. Okay, so we can conclude that isotonic solutions possess the same molar concentration. Okay, left hand side equals to right hand side, so same molar concentration. So let me write it here. Isotonic solutions possess the same molar concentration. Now let us see the definition of hypertonic and hypotonic solutions. Hypertonic and hypotonic solutions. When a solution has a higher osmotic pressure as compared to some other solution, it is termed as hypertonic solution. When a solution has a higher osmotic pressure as compared to some other solution is termed as hypertonic solution. So it's very easy, right? When a solution has a higher osmotic pressure as compared to other solution, it is hypertonic. The solution having lower osmotic pressure as compared to some other solution is referred to as hypotonic. So a solution having lower osmotic pressure having lower osmotic pressure as compared to some other solution is referred to be 1F is referred to as hypotonic solution. Okay, that a hypertonic solution is more concentrated and a hypotonic solution is less concentrated in comparison to a given solution. Now let us see what is the biological importance of osmosis. So, the phenomena of osmosis plays a significant role in the growth and survival of plants and animals. The bodies of plants and animals are composed of a very large number of externally small units called cells. A plant or animal cell consists of a fluid known as cell sap. The walls of the cell are made of living cytoplasmic membrane which is semi-permeable. The cell sap is usually quite concentrated and possesses a high osmotic pressure. When such a cell comes in contact with water or a hypotonic solution, that is solution having lesser osmotic pressure, osmosis takes place and water enters into the cell through the cytoplasmic membrane. This results in the swelling of the cell. On the other hand, if the cell comes in contact with a hypertonic solution, that is solutions having higher osmotic pressure, water moves from the cell to the solution due to osmosis. This results in the shrinking of the cell. Okay, the shrinking of the cell on account of osmosis is called plasmolysis. Osmosis is a regular feature in plants and animals. Several processes are regulated by osmosis in plants and animals. So let us see some important ones. Number one is the root of plants possess cells in which the cell sap is quite concentrated. Therefore, plants and trees absorb water from the soil through osmosis and push it up to their various parts such as stems, leaves, etc. Number two is the germination of seeds, stretching of leaves and flowers, growth of plants, etc. are also controlled by osmosis. Animals drink a considerable amount of water to quench the thirst. The water taken by the animal is absorbed by different parts of their bodies through osmosis. A 0.91% solution of pure sodium chloride known as saline water is isotonic with human red blood corpuscles. In this solution, corpuscles neither swell nor shrink. Therefore, medicines are mixed with saline water before being injected into veins. If red blood corpuscles are placed in distilled water or in some hypotonic solution, water flows into the cell. This causes the cells to swell and even to burst. On the other hand, if red blood corpuscles are placed in a hypertonic solution, that is 5% NaCl solution, water comes out of the cells and they shrink due to plasmolysis. So these are some important applications. There are many applications. Okay. So that's why this osmosis topic is very important. If you want to write what I have told or what I have discussed now, you can write in your own words. But it is very important. Now let us see some questions. A 5% solution of cane sugar, molecular weight 342 is given, is isotonic with 0.877% solution of urea. Solution of urea. Find the molecular weight of urea. So let's see the solution. Just now we have learned that for isotonic solution, for isotonic solutions, N1 by V1 is equals to N2 by V2. Molar concentration are same, right? Now, how many moles of sugars? Moles of cane sugar? It is weight by molecular weight, that is 5% solution. So 5 gram is there. So 5 by 342. This many moles of cane sugar. And volume of cane sugar? Volume of cane sugar solution this is 100 centimeter cube. 0.1 liter. So let us say let molecular weight of urea is m prime. So how many moles of urea? Moles of urea is weight is 0.877%. So 0.877 gram by molecular weight. Volume of urea solution? Volume of urea solution, that is 100 centimeter cube, that is 0.1 liter. Now if we substitute these values in this equation, we will have 5 by 342 divided by 0.1 is equals to 0.877 by m prime by 0.1. If you calculate m prime from this equation, you will get 59.99 gram per mole is the molecular weight of urea. Okay, so I think you got the point. Now moving forward to our next topic, that is abnormal molecular masses and Van 't Hoff factor. Okay. Now this is our last topic in the course of solution. So this is abnormal molecular masses and Van 't Hoff factor. See, we have seen that colligative properties, lowering in vapor pressure, elevation of boiling point, depression of freezing point, osmotic pressure. These colligative properties may be used for the determination of molecular masses of non-volatile solutes. The values of molecular masses thus obtained for several substances such as urea, sugar, glucose, sucrose are found to be same as expected from their chemical formula. However, this is not been found true in case of substances whose molecules associate or dissociate in solution. This is the biggest point. It has been observed that the molecular masses of such substances which undergo association or dissociation in solution determined on the basis of any of colligative properties are quite different from the normal values. If we take an example, the molecular mass of benzoic acid is found to be almost double of its normal value. Similarly, the molecular masses of NaCl is found to be almost half of the normal values. Such molecular masses are termed as abnormal molecular masses. Okay. So when we define abnormal molecular masses, the definition would be when the experimentally observed molecular mass of a substance determined on the basis of a colligative property is found to be different from the normal value as expected from its chemical formula, the observed molecular masses is referred to as abnormal molecular masses. Okay. Now if we notice association and dissociation of solute molecules. Now what is the cause of abnormal molecular masses? Cause of abnormal molecular masses. Cause of abnormal molecular masses. See, the cause of obtaining abnormal molecular masses is actually very simple. We have seen that colligative properties does not depend upon the chemical nature of solute. It depends only upon the number of particles. That's why it is colligative properties, right? Present in the solution. So we can say that delta is proportional to number of particles of solute. Okay, where delta represents the colligative property. It is colligative property. Colligative property. So we have already derived the expressions for calculating molar masses of solutes on the basis of colligative properties. So it is clear from those equations that the molecular mass of a solute is inversely proportional to a colligative property. So we can say molecular mass of solute is inversely proportional to colligative property, and this delta is number of particles of solute. So we can say it is inversely proportional to number of particles of solute in solution, right? Here we have to discuss three factors. Number one, when the molecular state when the molecular state of solute remains unchanged in the solution. So this is the first case when the molecular state of a solute remains unchanged in the solution. See, if the solute does not undergo any association or dissociation in the solution, the number of particles, that is number of moles of solute present in the solution, is the same as that added before dissolution. In this case, the colligative property has its normal value and the molecular mass obtained is the same as that expected on the basis of chemical formula. Thus, we do not get any abnormal molecular masses in this case. Non-electrolytic substances such as glucose, urea, sucrose, etc. behave this way. Okay, so if we talk about example, it will be glucose, non-electrolytic solutes, glucose, urea, sucrose, etc. are fall into this category. Okay, and their accurate molecular masses can be obtained with the help of any of the colligative property we have described. Number 2 is when the solute undergoes association in solution. So if it associates, then let us see what will happen. See, certain solute undergoes molecular association in solution. Two or more molecules of such solutes may combine together in solution to form aggregates. When two molecules of solute combine together, the aggregate forms is called dimer, and if three molecules aggregate together, then it is trimer. The aggregates, and if four molecules combine, then it is tetramer. So let us see one example. When benzoic acid is dissolved in benzene, two molecules of it associate together to form a dimer. Okay, when benzoic acid, we have already seen this example in the previous section. Dip into benzene, it will form a dimer. It will form a dimer. In the dimer thus formed, the two molecules of benzoic acid are held together by this dimer, are held together by hydrogen bond. If we show this, it will look like this: C6H5, C double bond O, single bond OH. This is hydrogen bonded with another benzoic acid, H O C double bond O, it will hydrogen bond, create hydrogen bond, C6H5. In this case, the formation of dimer reduces the number of solute particles, right? Which is obvious, to 1/2 of the number which would have been present had there been no association, because the process involves the formation of a single large particle from two smaller particles. Since the magnitude of a colligative property depends upon the number of solute particles in solution, the observed value of colligative property would decrease. The molecular mass of a solute is inversely proportional to the observed value, right? And hence observed value of colligative property, hence the observed value of molecular mass will be higher than the expected one. Thus, association of solute particles always leads to a higher value of observed molecular mass of the solute. This is the thing you have to note. Association of solute particles always leads to a higher value of observed molecular mass of the solute. Okay. If we take an example, in case of benzoic acid dissolved in benzene, the molecular mass of benzoic acid obtained on the basis of colligative property is almost double of the normal value because number of particles in solution reduces to almost one half due to formation of dimer. Now our number 3 point is when the solute undergoes dissociation in solution, what will happen? See, the electrolytic substances such as NaCl, KCl, BaCl2, these things are dissociate into ions when dissolved in water. The dissociation of a substance into ions increases the number of particles of solute present in the solution, which is obvious, right? If we take example of KCl, the solid, this is 1 mole added in water, aqueous, will give K plus aqueous, this is 1 mole, and Cl minus aqueous, this is 1 mole, so 2 mole. It is dissociated. The dissociation, okay, if the dissociation of KCl is taken to be equal to 100%, 1 mole of KCl would give 1 mole of K plus ions and 1 mole of Cl minus ions in solution. Thus, we would have 2 moles of particles in the solution. An increase in the number of particles of solute due to dissociation leads to an increase in the magnitude of the colligative property, and therefore a lower value of molecular mass is obtained. So we can note that the dissociation of solute in solution always leads to a lower value of observed molecular mass of the solute. The molecular mass of KCl obtained on the basis of any of the colligative property is half of the normal value because the number of particles gets doubled in solution on account of its dissociation into ions. So what we can do to solve this type of difficulties? That's what came Van 't Hoff factor. Van 't Hoff factor. This is I, represented by I. Van 't Hoff in 1886 extensively studied the phenomena of molecular association or dissociation of a solute in the solution and its effect on the colligative properties. He introduced a factor called Van 't Hoff factor, okay, to express the extent of association and dissociation of a solute in the solution. And if we want to define Van 't Hoff factor, the definition is the ratio of the observed, that is experimental, value of a colligative property to the normal or calculated value of the same property is termed as is termed as Van 't factor. Van 't factor I. So mathematically we can say I is observed, that is experimental value of a colligative property by normal or calculated value of the same colligative property. The same colligative property. Okay. So we can say I is delta observed by delta calculated. That's how we can remember. Okay. And for lowering of vapor pressure, I is delta P observed by delta P calculated. For elevation of boiling point, for elevation of boiling point, I is delta TB observed by delta TB calculated. For depression of freezing point, I is delta TF observed by delta TF calculated. And for osmotic pressure, for osmotic pressure, I is phi observed by phi calculated. That's how we can use the definition of Van 't factor to calculate all these things. See, we know that colligative property is proportional to number of particles of solute, right? So we can say delta observed is proportional to number of particles present in the solution. Present in the solution. And delta calculated is proportional to normal number of particles. So this equation delta observed by delta calculated, we can say I is delta observed by delta calculated by number of particles present in the solution by normal number of particles. And further we know that molecular mass of a solute determined on the basis of colligative property is inversely proportional to the colligative property. So on the basis of this we can say delta observed is inversely proportional to molecular mass observed and delta calculated is inversely proportional to molecular mass calculated. Okay. So this equation will reduce to I is delta observed by delta calculated is inversely proportional to, so m prime calculated by m prime observed. Okay. So calculated m prime means number of particles that is equals to number of particles present in the solution by normal number of particles. So this is equals to number of particles present in solution by normal number of particles. So this is the equation we will use. Okay. Now see, on basis of this, Van 't Hoff factor may also be defined as the ratio of normal molecular mass of a solute to its observed molecular mass. So we can say I is normal molecular mass by observed molecular mass. Okay. So from this we can say normal molecular mass is I into observed molecular mass. The value of I depends upon the molecular state of a solute in solution. Okay. So in this case we can say that when the molecular state of solute remains unchanged in solution, that is solute undergoes neither dissociation nor association, in that case I is 1. So we have three cases. Number one case is when the molecular state of solute remains unchanged in solution, that is solute undergoes neither dissociation nor association in that case I is 1. Number 2 case is when solute undergoes association. In that case I is less than 1. Number 3 case is when solute undergoes dissociation. I will be greater than 1. Okay. So if we include this Van factor, the equations will be revised as for lowering or relative lowering of for relative lowering of vapor pressure, this is revised as P naught minus P by P naught is I into X solute, chi solute. Okay. And for elevation of boiling point, the equation will be delta TB is I into KB into M. For depression of freezing point, delta PF is I into KF into M. For osmotic pressure, IV should be I into N RT. Okay. And remember this delta TF, this delta TB, this pi in this equation represent the observed value of the respective colligative property. Okay, remember this. All these are observed value. Now, if you want to find out the extent of dissociation and association of a solute in a solution, so let's see. Calculation of extent of association or dissociation of a solute in solution. The Van factor I enables us to calculate the extent to which a solute associates or dissociates in the solution. The extent of association is calculated in terms of degree of association, while that of dissociation is termed as degree of dissociation. So let us first see calculation of degree of association. Degree of association. Okay. So degree of association. Degree of association is defined as the fraction of the total number of moles of solute which undergoes association in the solution. So degree of association is defined as the fraction of the total number of moles of solute which undergoes association. So we can write it as degrees of association is alpha, that is number of moles of solute undergoing association divided by total number of moles taken. Okay. Suppose n molecules of a solute A associate to form an aggregate AN. So we can represent this as, let us say, n molecules of A associates and it forms an aggregate AN. Initially we have 1 mole of A and alpha is the degree of association. So at equilibrium we can say, at equilibrium we can say number of moles of A left unassociated is 1 minus alpha, and number of moles of AN is alpha by N. So we can say total number of moles present in solution is 1 minus alpha plus alpha by N. See, we have already seen that Cantor factor I is m prime calculated by m prime observed. That is equal to number of particles in solution by normal number of particles. Okay. Now we can say that I is equals to m prime calculated by m prime observed, that is equals to 1 minus alpha plus alpha by n divided by 1. Okay, because initially 1 mole of A, we have 1 mole of A, capital A, right? So m observed is 1. Or we can say m prime calculated by m prime observed is 1 minus alpha plus alpha by n, or 1 minus m prime calculated by m prime observed is alpha minus alpha by n. So we can say m prime observed minus m prime calculated by m prime observed. If we take alpha common, 1 minus 1 by n. So it will be alpha into n minus 1 by n, or we can say alpha is equals to m prime observed minus m prime calculated by m prime observed into n by n minus 1. So if we know all the values, we can calculate degree of association. Okay, now let us see for number 2, that is degree of dissociation. Okay, so number 2 is calculation of degree of dissociation. See, degree of dissociation is defined as the fraction of the total number of moles of solute which undergoes dissociation in the solution. So degree of dissociation can be defined as, let us say alpha is degree of dissociation, and that is number of moles of solute undergoing dissociation divided by total number of moles taken. Suppose an electrolytic substance A dissociate it in solution to give a total number of n ions and establish an equilibrium. So let us say A dissociates into equilibrium in this manner: N1B, N2C, in this manner, where we can say N1 plus N2 plus this is your total number of moles. and these B and C are ionic species formed on account of the dissociation of substance A, right? Now, again, in the similar manner, if we start with 1 mole of A and alpha is degree of dissociation, so at equilibrium we can say at equilibrium we can say number of moles of A left undissociated is 1 minus alpha, and number of moles of ions formed is n alpha. So we can say total number of moles present in solution is 1 minus alpha plus n alpha. We know Banto factor, that is I equals to number of particles in solution by normal number of particles. Okay, so this should be 1 minus alpha plus n alpha divided by 1, or we can say I minus 1 is n alpha minus alpha, that should be alpha into n minus 1, or we can say alpha is I minus 1 by n minus 1. Okay, remember this equation, very important. Now see, we know that I is, we know that I is m prime calculated by m prime observed. So alpha would be m prime calculated by m prime observed minus 1 by n minus 1. So alpha is m prime calculated minus m prime observed by m prime observed into n minus 1. Okay, so by these equations we can calculate degree of association or degree of dissociation. Now let us see some questions regarding this, otherwise the concept would not be clear. So let us see this question. The freezing point of a solution containing 0.2 gram of acetic acid in 20 gram of benzene is lowered by 0.45 degrees Celsius. Calculate the degree of association of acetic acid in benzene. Kf for benzene is given 5.12 Kelvin kg per mole. Let's see the answer. So here, freezing point of a solution containing 0.2 gram of acetic acid in 20 gram of benzene is lowered by 0.45 degrees Celsius. Calculate the degree of association of acetic acid in benzene. We know that acetic acid forms a dimer in benzene, right? And let us say degree of association is alpha. So twice acetic acid in equilibrium, they will form dimer Cbse whole 2. Initially, acetic acid is 1 mole and it is 0. And at equilibrium, this is 1 minus alpha moles because degree of association is alpha, and this is alpha by 2 moles. Okay. So from this we can say total number of moles present in solution at equilibrium is 1 minus alpha plus alpha by 2. And we know Van der factor I is number of moles of solution divided by number of moles taken, that is normal number of moles taken. It is 1 minus alpha plus alpha by 2 by 1, that is 1 minus alpha by 2, right? And molar mass of acetic acid CH3COOH is 60, and we know molality M is number of moles of solute divided by mass of solvent in kg. So it is 0.2 given 0.2 by 60 is the molar mass of acetic acid divided by 20 solvent given and by 100 molar mass. Okay. See the pages are, you see 20 gram of benzene, okay, and 0.2 gram of acetic acid. Now you can say after calculating you will get 0.167, and it is given that delta TF is 0.45 degrees Celsius, Kf is given 5.12 Kelvin kg per mole, delta TF is given. Delta TF we know I into Kf into molality. So putting all the values 0.45 equals to 1 minus alpha by 2 into 5.12 into 0.167. So if you calculate alpha, from this you will get 0.948. That is, degree of association of acetic acid is 94.8%. This implies I is 94.8%. Okay, that's how you have to solve this type of problem. Now let us see our okay. I think that's all for this chapter. I think तुम लोगों को ये समझ में आ गया होगा, ठीक है. What I have tried to explain each and every point of this chapter, because this chapter is extremely important in concept wise, because if your concept do not clear, if you do not clear your concept in this chapter, then you will definitely trap into JEE NEET and board examination questions. So this chapter is very lengthy and it is very conceptual. So I have tried to clear every concept what is needed to learn. So I hope all of you have liked it. Kindly like, share and subscribe. तुम लोग जब सब्सक्राइब करते हो, कमेंट करते हो, तो हम लोग को उत्साह मिलता है कि मैं और भी तुम लोग के लिए वीडियो बनाऊं. कमेंट सेक्शन में तुम लोग कमेंट करो कि और कौन सा चैप्टर का वीडियो तुम लोग को चाहिए, इस टॉपिक का वीडियो तुम लोग को चाहिए, फिजिक्स केमिस्ट्री मैथ, कोई भी चैप्टर का, कोई भी टॉपिक का, कौन सा चैप्टर का वीडियो चाहिए, आई विल अपलोड दैट. ओके, सो थैंक यू and have a good day.